Hello and welcome to the Snoozy Scientist. I'm really glad you made it here tonight. Wherever you are, whether you're lying in bed, curled up on the couch, or watching waves from a window, this quiet corner of the internet was made just for you. A soft space to unwind and wonder. Tonight, we're going to explore the brutal physics behind tsunamis, what really causes them, the violent chain reactions beneath the seafloor, and why they're far more dangerous than most people think. Tsunamis are among the most misunderstood forces on our planet. They're not just big waves, they're walls of water triggered by physics so powerful that they can move millions of tons of ocean in seconds and drop it on a city. They cross oceans silently at a very high speed that they're barely noticeable until it's almost too late. Triggered by earthquakes, landslides, or volcanic eruptions, a tsunami can carry the energy of thousands of nuclear bombs at a speed faster than a jet. This isn't just about water, this is about kinetic energy, momentum, wave mechanics, and what happens when Earth's most powerful forces meet fluid dynamics under pressure. And the result is one of the most violent natural disasters on the planet. If you think you understand tsunamis, think again, because the physics behind them is terrifying. Tonight, we'll walk through the raw physics of rupture, displacement, speed, and impact, and we'll uncover how something so silent can become so deadly, so fast. If you're already settling into this quiet moment, it would mean the world if you gently liked the video or subscribed if you'd like more bedtime explorations like this. And if you don't mind sharing, I'd love to know, where in the world are you winding down from tonight? What time is it there? It's always beautiful to see this quiet little map of dreamers lighting up across the globe. So now, take a deep breath. Let your shoulders soften, and let's begin. So, what exactly is a tsunami? Most people hear the word and imagine an enormous wall of water curling like a stormy ocean wave, towering over a city's skyline. But that image, while dramatic, isn't exactly how tsunamis work. To really understand their power, we first need to separate them from the kinds of waves we're used to seeing at the beach. Normal waves, the kind that tumble across the shoreline and crash into piers, are surface waves. They're born from the wind. As air moves across the ocean's surface, it drags the top layer of water along with it, creating ripples that grow into swells. These waves are relatively shallow, usually only affecting the upper few meters of water. They roll and tumble, but their energy is limited to the surface, and their wavelengths, the distance between one crest and the next, are short. Most are under 100 meters. Tsunamis, though, are a completely different creature. They're not caused by the wind. They're caused by movement. Sudden, massive movement. When the seafloor shifts, whether from an earthquake, a landslide, or a volcanic eruption, it doesn't just disturb the water at the surface. It displaces the entire column of water above it, from the ocean floor all the way to the surface, often across an enormous area. Imagine lifting the bottom of a bathtub in one violent jolt. The water doesn't just ripple, it lurches. That's what makes a tsunami so different. It's not a wave that dances across the top of the sea. It's the entire ocean in motion, and the scale of that motion is hard to grasp. A tsunami's wavelength isn't a few meters or even a few hundred. It can be hundreds of kilometers long. Picture a single wave stretching from one coastline to another, entire countries apart. From crest to crest, a tsunami can span the entire length of an ocean basin. But because the wave's energy is distributed through the entire depth of the ocean, it doesn't look dangerous at first. Out at sea, a tsunami might only rise half a meter above the surface. To the naked eye, it can appear as nothing more than a gentle swell, barely noticeable among the normal movements of the ocean. Boats may rise slightly, then settle again, unaware that they're riding a wave that's moving at the speed of a jetliner, over 500 miles per hour. But here's where it becomes terrifying. As the tsunami approaches land, everything changes. The ocean shallows, the wave slows, and as it slows, its energy, conserved but compressed, begins to rise. That seemingly harmless swell begins to pile upward, lifting more and more water into a growing wall. The wavelength shortens, the height grows, and what once moved invisibly beneath ships now becomes a violent, rushing mass of seawater crashing inland with unstoppable force. It's important to note that a tsunami isn't just one wave, either. It's a series of waves, often several, sometimes dozens, arriving minutes or even hours apart. The first may not be the biggest. In fact, survivors often report a strange calm after the first wave, only to be caught off guard by an even larger surge that follows. The water retreats, exposing seafloor, drawing people closer, and then returns with terrifying force. It's this behavior that makes tsunamis especially dangerous. Their rhythm doesn't follow the patterns we're used to. There is no steady pulse, only chaos and force. One of the most persistent myths is that tsunamis are just big waves. But in truth, they are unlike anything the ocean typically produces. They're not born from storms. They don't crash and curl like wind-driven surf. They are massive energy pulses that move through the ocean, not just on top of it. Imagine pressing your hand into the middle of a full bathtub and watching the water shift all at once. That's the physics at play, except on a scale that spans thousands of kilometers and with the energy of thousands of atomic bombs. The Japanese word tsunami literally translates to harbor wave. It comes from the tragic irony that these massive waves often go unnoticed in deep water, only revealing their true size and power once they reach coastal areas where people live, work, and sleep. It's not just the water height that matters, it's the volume, the sheer mass of water in motion. When a tsunami hits, it doesn't just knock things over, it lifts buildings off foundations. It uproots trees, it tears bridges in half. The water doesn't flow around obstacles, it crushes them. The force is not just at the front of the wave, it's in the momentum behind it and the endless surge of water that keeps coming after the initial impact. As we continue, we'll explore what actually sets this motion into play, what happens far beneath the ocean's surface in those critical seconds when the Earth's crust gives way, and how that one violent shift triggers a chain reaction that transforms a calm sea into one of the deadliest forces on Earth. Beneath the calm, glistening surface of the ocean, something vast and invisible is always moving. The Earth's outer shell, what we walk on, build on, and take for granted, isn't one solid piece. It's broken into massive sections called tectonic plates. Imagine a giant puzzle covering the surface of the planet, with each piece slowly drifting, grinding, and pushing against its neighbors. These pieces float on top of the mantle, a layer of hot, slowly flowing rock deep below. And while they move at only a few centimeters per year, about the speed your fingernails grow, that movement is anything but gentle. Where two plates meet, the Earth's true power reveals itself. Most of the world's most powerful earthquakes and tsunamis don't begin in the middle of the ocean or along smooth coastlines. They begin in very specific places called subduction zones. These are areas where one tectonic plate is being forced beneath another, where oceanic crust dives under continental crust or another oceanic plate. It's not a smooth slide, it's more like a slow grinding battle with unimaginable amounts of pressure building over time. In these zones, the descending plate doesn't simply sink away into the mantle. It sticks, it jams, it locks itself in place against the overriding plate. But the movement of the plates never stops. So while the top plate tries to stay still, the bottom one keeps pushing for years, decades, even centuries. And as that pressure builds, the seafloor above begins to warp. You can't see it from above. Boats drift peacefully, fish swim by undisturbed. But slowly the crust is bending, bowing upward, storing energy like a spring pulled tight. Every meter of movement means tons upon tons of rock being deformed and displaced. And all of that tension is quietly waiting, waiting for the moment it finally slips. The locked zone can stretch for hundreds of kilometers. Imagine two slabs of rock the size of continents, grinding together with nowhere for the energy to go. When the pressure finally becomes too much, it doesn't ease off gently. It snaps. That sudden rupture, the violent release of energy stored over centuries, is what triggers the earthquake that sets everything else in motion. But the earthquake itself is only part of the story, because when the crust rebounds and the seafloor shifts, it pushes an enormous column of water upward, not just on the surface, but through the entire depth of the ocean. And that's the moment when a tsunami is born. In some subduction zones, the seafloor can rise or fall by several meters in an instant. That's like lifting a city sized platform under the ocean in the blink of an eye. The water above, suddenly displaced, rushes to fill the gap. But because water doesn't compress, that motion becomes a wave that stretches out for hundreds of kilometers in every direction, fast, wide, and nearly invisible at first. The most dangerous subduction zones are located in places like the Pacific Ring of Fire, an arc of deep sea trenches, and volcanic activity circling the Pacific Ocean. Here, the Pacific Plate and several smaller plates are constantly colliding with the plates of Asia, the Americas, and the islands in between. In these zones, the tectonic energy is so concentrated that many of the largest tsunamis in recorded history have been born from their depths. What makes subduction zones especially deceptive is how still they can seem. These aren't areas where daily tremors shake buildings or raise alarms. Some of them remain quiet for hundreds of years, giving coastal communities a false sense of safety. But every day that passes without a quake is another day the pressure increases. The spring winds tighter, and when it finally snaps, it doesn't give a warning. This slow, hidden buildup of energy is why scientists sometimes call subduction zones tectonic time bombs. They are quiet until they're not, and when they go off, the impact isn't just local, it can ripple across entire oceans. While the surface world continues its daily rhythm, planes taking off, children playing on beaches, ships cutting across shipping lanes, miles below, the planet is still shifting. Plates keep pushing, pressure keeps rising, and the next snap might already be on its way. From here, it's only a matter of time before that built up strain turns into motion. And when it does, it unleashes more than just shaking ground. It releases a surge of force that can ripple through the ocean at jet speed. But to understand how that moment unfolds, we first have to look at what happens when the crust actually breaks apart, when the earthquake hits and the ocean begins to rise. All it takes is a moment. After centuries of pressure, the fault line gives way. When the tectonic plates beneath the ocean lock together at a subduction zone, they aren't just resting quietly, they're holding back an immense, relentless force. One plate is pressing downward and forward, while the other resists wedged tightly against it. Over time, they deform. The upper plate starts to bulge, flexing under the stress. Like a wooden board slowly bending under weight, it stores energy invisibly, quietly. But the Earth has a limit, and when that limit is reached, the plates rupture. Not slowly, not gradually, suddenly. The locked boundary breaks free, and the crust rebounds with incredible force. This is the earthquake, and unlike the gentle rolling tremors some people associate with seismic activity. Subduction zone quakes can be brutally violent. In these moments, the ocean floor itself jerks upward or downward in just seconds. The shift might be several meters, enough to raise entire sections of seabed abruptly and violently. It's this vertical displacement that becomes the catalyst, because when the seafloor moves, it forces the water above it to move too. The result isn't just a splash or ripple, it's a massive instant uplift of ocean. To understand the scale, imagine the ocean being punched from below by a wall of solid rock. The water, unable to compress or absorb the blow, is thrown upward and outward. This isn't like wind pushing the surface. The entire water column from the seafloor to the surface is set in motion. That movement forms the wave, not just on top, but throughout its entire depth. In the first few seconds, it doesn't even look like a wave. There's no crest curling above the waterline, no obvious swell. The ocean surface may rise slightly, almost imperceptibly, over a distance of hundreds of kilometers. But underneath, the energy is racing outward, fast and deep, carrying with it the raw signature of the quake that set it off. Scientists watching this in real time don't see the tsunami wave immediately. What they see first is the seismic data. Earthquakes of this kind are recorded almost instantly by global networks of seismometers, highly sensitive instruments that detect the slightest motion in the ground. On screens in monitoring centers around the world, a flurry of data appears: jagged lines, spike patterns, timestamps. Within seconds, computers begin triangulating the location of the rupture. From the first shudder on the seabed to the full release of energy might take only 30 to 60 seconds, but that's enough to alter the shape of the coastline, lift entire islands, and send out tsunami waves in every direction. Visual simulations created using real seismic readings can now show us what happens beneath the waves with startling precision. On screen, a map of the seafloor lights up with pulses of color. A bright, fast-moving distortion expands outward like a ripple in a still pond, except that ripple is dozens of kilometers wide, and it's traveling as fast as a passenger jet. The vertical motion of the quake is key. Horizontal shaking may be destructive to buildings on land, but it's the vertical jolt where one side of the fault lifts or sinks that physically displaces the ocean. And when that displacement covers hundreds of kilometers of seabed, it's no longer just a local event. The wave it generates can cross entire oceans. This rupture doesn't only send waves across water, it also sends shock waves through time. In a matter of seconds, the tectonic struggle that's been building silently for centuries finds its violent release, and everything changes. And while that energy races across the ocean floor, still mostly invisible to the human eye, it is already transforming into something far more dangerous: an unstoppable, fast-moving wall of momentum. To understand just how fast and far that energy can travel, and why tsunamis can strike without warning on distant shores, we have to follow that wave into the deep ocean where the true speed of destruction begins. The ground doesn't always need to split apart for a tsunami to begin. Sometimes it's the mountains beneath the sea or along its edge that suddenly give way. While many tsunamis are born from the violent rupture of tectonic plates, others begin from entirely different kinds of chaos: explosive volcanic eruptions, or massive landslides that shove billions of gallons of water out of place in an instant. Volcanoes don't just live on land. In fact, more than three-quarters of the world's volcanic activity happens underwater. Along the mid-ocean ridges and at the boundaries of tectonic plates, magma constantly pushes upward, building entire mountains and islands that most people never see. When an undersea volcano erupts, it can trigger a sudden displacement of water, depending on the violence and speed of the eruption. These eruptions can blow a part of the seafloor or cause parts of a volcano's flank to collapse into the ocean, each of which is capable of generating a tsunami. But the most dramatic events often occur near the surface, where volcanic islands tower above the sea, their slopes steep and unstable. These island volcanoes are not just beautiful, they're geological time bombs. As they erupt and grow over time, their flanks can become overloaded with layers of lava, ash, and fragmented rock. The weight builds, and deep within, the heat and gas pressure continue to rise. Sometimes that pressure is released with explosive force. A portion of the volcano can suddenly collapse, sometimes into the sea, sometimes under its own weight. And when this happens near or underwater, the result is devastating. The collapse sends a massive wall of debris crashing into the ocean, and in doing so, it pushes aside an enormous volume of water almost instantly. Imagine dropping a stone into a bathtub, but instead of a stone, it's a chunk of mountain the size of a city. The water reacts immediately, surging outward in all directions. These aren't waves created by wind or surface friction. These are massive surges of energy generated by brute force, what scientists call displacement waves. And depending on the size and speed of the collapse, they can be many times larger than earthquake-driven tsunamis. These types of events are rare, but they're powerful enough to earn their own name, mega-tsunamis. One of the most well-known examples comes from a remote corner of Alaska. In 1958, a massive rockfall in Lituya Bay triggered a wave so large it stripped trees from hillsides 500 meters above sea level. It wasn't a traditional tsunami that traveled across oceans, but it was a stark example of what happens when a sudden mass of rock hits water at high speed. The energy doesn't just disappear, it has to go somewhere, and in this case, it went up, then outward. Volcanic island collapses can do something similar, but on a much larger scale. In the Canary Islands, scientists have studied the ancient flanks of volcanic slopes that appear to have broken off in the distant past. The debris from these collapses stretches across the ocean floor for hundreds of kilometers. If such an event were to happen again in modern times, simulations show that a wave could travel across the Atlantic, reaching distant coastlines in hours. The same threat exists in regions like Indonesia, where steep volcanic islands rise from deep waters. In 2018, part of the Anak Krakatau volcano collapsed into the sea after a major eruption. The resulting tsunami struck nearby coastlines with almost no warning, killing hundreds of people in the middle of the night. There was no massive earthquake to trigger it, just the silent, sudden collapse of part of a mountain. Even underwater landslides, events that may never reach the surface, can produce tsunamis if enough material shifts quickly. These slides may happen after an earthquake weakens a slope, or after years of sediment buildup reaches a breaking point. When the side of an underwater ridge or continental shelf fails, it can create a wave powerful enough to reach nearby shores within minutes. What makes these tsunami triggers especially dangerous is how fast they happen and how little warning they give. There's often no shaking to alert anyone, no tremor on land, just the sudden movement of earth and rock and the brutal physics of water reacting to it. And once that energy has been released into the sea, it doesn't matter how it started. Whether it began with fire, rock, or collapse, the result is the same, a pulse of raw energy that begins racing across the ocean, fast and silent, and heading for shore. Once a tsunami is triggered, whether by earthquake, volcanic collapse, or landslide, something remarkable and terrifying happens. The ocean becomes a messenger of destruction, carrying that initial burst of energy across vast distances with almost unimaginable speed. Deep beneath the surface, the wave begins its journey, and it does so not slowly, but at speeds that rival a jet airplane. In the deep ocean, where water depths can reach thousands of meters, Tsunamis can travel between 500 and 800 kilometers per hour. That's the cruising speed of a commercial jetliner, fast enough to cross entire oceans in less time than it takes most people to drive across a city. But despite this incredible velocity, a tsunami out in open water is almost invisible. If you were on a ship directly above it, you might not even notice. This is because in deep ocean, the energy of a tsunami is distributed throughout the entire water column, from the surface all the way down to the seafloor. The wave may only be a meter or less in height, and its slope is so gentle that it blends into the normal rhythm of the sea. There's no towering wall of water, no crashing surf, no roar, just a long, broad hump moving quietly beneath you, so wide and smooth that it looks like nothing at all. That's one of the most deceptive things about tsunamis. They carry incredible energy, but they wear a mask of calm while crossing the ocean. Traditional waves, like the ones surfers ride, are shaped by the wind and travel only across the surface. They have short wavelengths, maybe 30 to 100 meters from crest to crest. Tsunamis, on the other hand, have wavelengths that can stretch hundreds of kilometers. From a satellite view, they appear as a slight bulge, barely perceptible, but in motion. And to understand how fast they really are, imagine this: a tsunami triggered off the coast of Chile could reach Japan in about 22 hours. One originating in Alaska could strike Hawaii in less than 6, and a wave that begins near Indonesia might give the west coast of the United States just 14 to 16 hours of warning, barely enough time for alerts to go out, let alone for cities to prepare. Their ability to move silently and quickly makes tsunamis unlike any other natural hazard. Earthquakes, even large ones, are typically over in a matter of minutes. Hurricanes give days of warning, but tsunamis ride the deep sea like a ghost, fast, quiet, and far reaching. Even more alarming is how little friction they encounter in the open ocean. Unlike waves that break and scatter energy when they interact with wind or obstacles, a tsunami glides along with minimal resistance. Its energy isn't easily lost. The ocean acts almost like a conveyor belt, allowing the wave to retain most of its momentum as it travels. And because it doesn't lose much speed or power while moving through deep water, the danger isn't diminished by distance. Another way to visualize their speed is through air travel. The average commercial airplane flies around 850 kilometers per hour. A tsunami at full speed is only slightly slower. But while a jetliner leaves behind a trail of noise and vapor, a tsunami leaves nothing but silence until it hits shallow ground. It's like an invisible arrow released from a bow, silent in flight, but devastating on impact. And unlike airplanes, tsunamis don't follow predictable routes. They fan outward from the point of origin, traveling in all directions. As they spread, they interact with underwater mountains, ridges, and ocean basins, which can deflect, reflect, or even focus the waves like lenses. This means that areas thousands of kilometers from the source might still be in the path, and sometimes those distant places bear the brunt of the force. It's this combination of stealth and speed that makes tsunamis so deadly. They defy the senses. Nothing in the natural world prepares the human brain to think of a wave as fast as a jet and as wide as a mountain range. People on distant shores may not feel a single tremor, hear any roar, or notice any change until the wave begins to rise. But by the time the sea pulls back from the shoreline and the ground begins to rumble with strange vibrations, the wave is already upon them. Not because it came from nearby, but because it traveled like a missile, thousands of kilometers across the open sea, fueled by physics, guided by nothing but the shape of the ocean floor, and moving with the silent urgency of a predator that never slows down. And when the ocean begins to change shape, when the water no longer behaves like water, That's when the true nature of this speed begins to show. Because even though the wave itself may have been quiet and smooth for most of its journey, the moment it meets shallow water, everything changes. The speed, the depth, and the energy that's been quietly hiding below the surface all start to shift at once. As the tsunami rushes forward across the deep sea, the reason it remains so silent and deceivingly gentle lies in how its energy is stored and distributed. Unlike surface waves created by wind, those rolling frothy crests that people see at beaches, tsunamis behave very differently. Their energy isn't confined to the upper layers of the ocean. Instead, it stretches through the entire depth of the water column, from the surface all the way to the seafloor. This is what gives a tsunami its unique power. Picture a cross section of the ocean. A normal wind driven wave might stir the top 100 meters or so, but a tsunami can move water all the way down through depths of 4,000 meters or more. It's like a giant, invisible slab of water shifting in unison, not just dancing across the top. This vertical profile of motion means that the wave is carrying a massive volume of water with it, not just on the surface, but throughout the entire depth. And with that volume comes inertia. It becomes a vast engine of kinetic energy gliding just beneath the visible world. Tsunamis also have extraordinarily long wavelengths. From one wave crest to the next, the distance can range from tens to hundreds of kilometers. These waves are so stretched out that their slopes are very gentle, giving them a deceptively flat appearance. They're less like a ripple and more like a slow, heaving rise and fall of the entire ocean. But despite their subtle appearance, each of these waves carries the stored energy of violent geological events, energy that doesn't simply vanish as the wave travels. This is where tsunamis differ most dramatically from wind waves. Wind waves lose energy quickly. They're scattered by opposing winds, dispersed by rough water, and absorbed by obstacles. In contrast, tsunami waves are incredibly efficient at conserving energy because they engage the full depth of the ocean and move with long, slow wavelengths. There's very little resistance to sap their strength. The ocean acts like a superhighway, allowing them to glide effortlessly across entire basins. You could think of it as the difference between a pebble skipping across a pond and a freight train rolling across smooth tracks. The pebble makes a splash, but quickly loses its momentum. The train, once in motion, carries on for miles without needing more force. A tsunami is the ocean's freight train, steady, massive, and largely unstoppable once it begins moving. This ability to hold energy over long distances is what makes distant tsunamis so dangerous. A wave that begins off the coast of Alaska can still strike Japan, Hawaii, or California with tremendous force. Its energy barely diminishes during its journey because there's so little in the open sea to slow it down, and the water's depth acts like insulation, protecting that energy from being scattered. When these waves eventually reach shallower coastal areas, all of that deep water energy is suddenly compressed. The speed decreases due to friction with the seafloor, but the energy must go somewhere. It has to rise. This is when the wave begins to grow in height, often dramatically, as its once gentle slope transforms into a wall of water. What once looked like a harmless ripple far offshore becomes a towering surge of destruction as it approaches land. It's during this stage, when the wave begins to build, that people often turn to coastal defenses for protection. Seawalls, breakwaters, and artificial reefs are commonly constructed to reduce the impact of normal waves. These structures are designed with everyday wave behavior in mind, mostly focused on wind-generated waves that affect only the top of the water column. But tsunamis are not everyday waves. Their energy isn't concentrated on the surface, which makes these traditional barriers far less effective than expected. Because tsunami waves extend to the ocean floor, their energy passes underneath most wave-blocking structures. A seawall might be several meters tall, But if the tsunami is pushing water from top to bottom, it can simply flow beneath the wall, around it, or even over it entirely. The volume and mass behind a tsunami are far too great to be stopped by surface level engineering. In fact, in many places, seawalls have been overtopped or rendered useless simply because the wave's force exceeded what the structure was designed to handle. Some barriers even end up reflecting wave energy in unintended ways, channeling it into narrower paths and amplifying the impact on vulnerable coastal zones. This is why tsunami resistant infrastructure has to be designed with an entirely different kind of wave in mind, one that doesn't just brush the surface, but churns the ocean's entire body. Understanding how tsunami energy behaves from the wavelength that stretches beyond the horizon to the deep water momentum that never seems to fade is crucial to grasping the full scale of the danger. And it's only when we follow this energy from its source beneath the sea to its transformation at the shore that we start to see just how complex and brutal the physics behind tsunamis truly is. And as that silent freight train of water nears the coastline, its deep energy begins to rise, not just in height, but in fury. The shape of the seafloor beneath it is about to play a defining role in how that energy unfolds, because what lies beneath the surface as the wave approaches land will determine just how devastating the final strike becomes. As the tsunami races toward shore, still invisible to the untrained eye, something eerie begins to happen. The sea, moments ago calm and familiar, starts to retreat. It doesn't just lower with the tide, it vanishes in great swaths. Fish are left flopping on the bare sand. Boats rest awkwardly on dry ground. Curious beachgoers inch forward, phones in hand, drawn toward the exposed ocean floor like moths to a flame. But what feels like a marvel of nature is in truth one of its most chilling warnings, because when the ocean suddenly pulls back like this, it's not a sign of safety, it's a sign that the wave is coming. This withdrawal isn't a trick of the tide or a freak coastal illusion. It's a direct result of the tsunami's powerful physics. As the long tsunami wave approaches land, the shape of the wave determines what people see first. In some cases, the leading edge of the wave is a trough, not a crest. Imagine a massive ripple in the ocean, and the lowest point of that ripple is the first to arrive. When that trough hits shallow water, it acts like a vacuum, pulling seawater away from the shore and toward the deeper ocean. The shoreline is sucked dry, as if the sea is breathing in before a colossal exhale. This vacuum effect can expose hundreds of meters of seabed that are normally hidden, turning a crowded beach into what looks like an alien landscape. To the unaware, it can seem fascinating, an invitation to explore, but in reality, it's a countdown. The deeper the ocean pulls back, the more violent the wave that's about to follow. This phenomenon happens because of the way tsunami waves are shaped. They're not like wind-driven swells that rise and fall gently. They're part of a wave train that can span enormous distances from one crest to the next. So if the wave's leading edge is the low point, then the towering crest is right behind it, moving at high speed and gaining height as it enters shallower waters. There's no dramatic pause between the receding ocean and the incoming surge. Once the trough has passed, the crest rushes in, fast and hard. And by the time the water returns, there's no time left to run. The psychological trap is devastating. People see the sea pulling back and instinctively move closer to see what's happening. Children chase fish, parents follow with phones to capture the moment. But the tsunami isn't just a single wave, it's an entire mass of displaced ocean racing forward. And when that wall of water comes surging in, it doesn't care how many people are standing there watching. In places like Thailand and Indonesia, during the 2004 Indian Ocean tsunami, countless lives were lost simply because people didn't know what this strange phenomenon meant. The sea pulled back dramatically, and crowds rushed toward it. Within minutes, a massive wave came crashing ashore, sweeping away everything and everyone in its path. What makes this even more tragic is that the withdrawal is one of the most reliable natural tsunami warning signs we have. It's not something that requires satellites or buoys or high tech sensors. It's nature signaling in real time. Something enormous is coming. In fact, in some coastal regions with limited access to technology, this sign alone is used to trigger evacuation protocols. When the water disappears, people know to run inland, fast and without hesitation. This natural early warning doesn't happen with every tsunami. If the leading edge is a wave crest rather than a trough, the water may surge in without much warning at all. But when the ocean does recede, it's never a coincidence. It's not the tide. It's not the wind. It's the first visible edge of disaster. To understand how dangerous this can be, it helps to remember just how long tsunami wavelengths are. A single wave can be over 100 kilometers wide. So when the front end of the trough reaches shore and starts pulling water away, the rest of the wave is still far out at sea, but it's coming and it's moving fast. Once the crest rises into shallow water, the energy that's been building in silence suddenly becomes visible, violent, and unstoppable. This withdrawal doesn't just signal danger, it sets the stage for destruction. As the ocean floor is exposed, any natural defenses that might slow the wave are stripped away. Coral reefs and shallow sandbars that would normally break up incoming swells are left dry and useless. And when the wave finally returns, it slams into bare coastline with full force, facing little resistance. Even the ground underfoot may give a subtle clue. As the water rushes away, some coastal areas experience a strange trembling or low rumble, a sense of pressure shifting beneath the sand. But by then, there's barely time to react. The window between the retreat and the return can be just a few minutes, sometimes even seconds. And so, in those fleeting moments when the sea disappears, the safest place to be is far away and moving fast. Because what follows is not a wave as most people imagine it, but a rising wall of water fueled by a physics engine that began thousands of kilometers away. And just as the wave builds higher and stronger with each second, its transformation isn't done yet. Because now, as the shallows squeeze its energy upward, the tsunami enters its most dangerous phase, the moment when speed turns into height and silent force becomes towering flood. As the tsunami approaches land, something remarkable and terrifying begins to unfold beneath the surface. The speed it once carried across the deep ocean begins to slow, not by choice, but by physics. And yet, as its pace drops, its size begins to rise. What was once an almost invisible ripple out at sea begins to transform into a towering surge. This is the moment when the tsunami reveals its true form, and it all comes down to something called the shoaling effect. Out in the deep ocean, tsunamis travel fast but stay low. Their immense energy is distributed throughout the entire depth of the water column, often several kilometers deep. At that depth, there's plenty of room for the wave to carry its power horizontally. The ocean acts like a giant runway, letting the energy glide smoothly forward. But as that runway disappears, as the ocean floor rises and the water becomes shallower near land, the wave's energy has nowhere else to go but up. This is where shoaling begins. Shoaling is a natural consequence of how waves behave when they enter shallow water. It's not unique to tsunamis. Even regular waves do this to some extent. But with a tsunami, the scale is dramatically larger. In the deep ocean, a tsunami might measure only a meter or two in height, barely enough to stir a ship. But as it nears shore, that same wave can grow into a wall of water 10, 20, even 30 meters high, as tall as a 10-story building. The reason lies in energy conservation. A tsunami carries a fixed amount of energy, most of which is kinetic, tied to its motion and mass. In deep water, this energy is spread out vertically across the entire depth. But as the depth shrinks, that energy must be compressed. The horizontal space stays the same, but the vertical profile of the wave starts to rise. It's like squeezing one end of a tube of toothpaste. The pressure doesn't vanish, it simply moves and bulges outward. The steeper the coastline, the faster this amplification happens. If the seafloor rises sharply, the wave hits the wall and leaps upward quickly. If the slope is more gradual, the amplification happens more slowly, but can actually result in broader and more devastating inland flooding. That's because the energy is still there, and now it has more room to spread inland instead of upward. Visualize this in numbers. A tsunami that measures just 1 meter high in the deep ocean might not even be noticed by a passing ship, but as it approaches a coastline and enters water that's only 50 or 100 meters deep, that wave can grow dramatically. By the time it reaches water that's just a few meters deep near the shore, the wave's height can multiply 10 to 30 times. A wave that once crept silently beneath the sea can suddenly rise into a massive, fast-moving wall that crashes onto the coast with unimaginable force. And it's not just height that changes, it's shape. Shoaling also stretches and steepens the wavefront. Instead of a long, flat hump, the wave starts to rise sharply and curl forward, making it even more powerful as it hits obstacles like buildings, trees, or seawalls. The water behind the crest builds up, adding momentum and mass. By the time the wave reaches the shoreline, it's not just tall, it's heavy, fast, and unforgiving. This process can be visualized like a conveyor belt of water. As the belt slows down due to friction with the shallower seabed, the water coming behind has nowhere to go but up and over. It stacks and it builds, and that stacking effect continues until the wave finally releases all that stored energy onto the coast. The physics behind this are simple, yet devastating. It's a balance of energy and mass. The ocean doesn't lose energy as it shallows, it simply reshapes it. And what was once kinetic energy moving forward becomes potential energy rising upward. Then, as the wave breaks, that potential collapses back into motion, now aimed directly at everything in its path. That's why even areas that seem safe from normal waves can be caught off guard by tsunamis. Traditional wave barriers or seawalls are often built based on storm surges or tides. But a tsunami reshaped by shoaling is an entirely different beast, higher, faster, and carrying far more energy per meter than any storm surge. And the threat doesn't end at the shoreline. As the wave rises and breaks, it unleashes its power not only upward, but forward. The water rushes inland, carrying debris, battering structures, and tearing through communities. The same physics that once made the wave invisible in the open ocean now make it impossible to escape on land. And the moment that water begins to crash against shore, its energy has only just begun to transform again into motion, into destruction, and into a surge that refuses to be stopped. Because as the wave rises and races forward, it no longer behaves like something you'd see at the beach. It becomes a moving flood, a bulldozer made of water. As the tsunami moves inland, the shape it takes becomes even more unpredictable. Most people imagine a towering, curling wave, like something out of a surf competition, a dramatic crest of water rising high before crashing down. But in reality, tsunamis often don't look like waves at all. In fact, what many survivors describe isn't a wave, it's a sudden, rising wall of water. Or even more unsettling, a fast, churning surge that floods in like a river that forgot its boundaries. The reason for this is found in the geometry of the coast itself and the underwater shape of the land leading up to it. When the seafloor is steep and drops off quickly near the shore, the incoming tsunami doesn't have much room to spread out. Instead, the energy focuses upward and the wave rises sharply. This can create that dramatic towering wall of water, tall, steep, and crashing like a vertical blow. These are the images that tend to go viral, but they're not the most common version. More often, the coast doesn't drop off suddenly. Instead, the seafloor rises gently, sometimes for miles. In these cases, the wave has more time to spread and flatten, so instead of curling or breaking, it surges. It looks like the ocean itself is lifting and sliding onto the land. There may be no visible crest, no dramatic wall, just a fast, unstoppable flood that keeps pushing forward, gaining height and speed as it moves. The kind of wave that tricks people into thinking they have time until they don't. This is why tsunami warnings are so often misunderstood. People look at the ocean and they don't see a massive wave forming offshore, so they stay. They take photos. They underestimate the danger. But by the time the water starts pouring in, it's already too late. The wave has arrived. It just didn't look the way anyone expected. Even more confusing, the type of wave can shift dramatically depending on how the coast is shaped. A bay, for example, can act like a funnel. As the tsunami enters, the walls of the bay force the energy into a narrower space. The water is squeezed, rising even higher and speeding up. What might have been a gentle surge on a straight coast can turn into a steep, deadly wave inside a bay. The same principle applies to underwater features. Ridges, canyons, and seamounts lying just offshore can guide or bend the tsunami's energy, reshaping how it reaches the land. Some areas might barely notice the wave. Just a few miles away, another town might be completely devastated, all because the underwater terrain focused the energy in one direction and weakened it in another. It's like aiming a magnifying glass at a patch of sunlight. The light is the same, but the effect becomes concentrated. In flat coastal areas, the tsunami might not look like a wave at all. It might look like a fast-moving tide that just doesn't stop. The water rises and rises, sweeping across roads, pulling apart homes, and drowning everything in its path. In these cases, people often don't realize the tsunami has arrived until they're already waist deep in water, and by then, the current is too strong to escape. This wide variety in wave shape and behavior makes tsunamis especially difficult to predict visually. Two places on the same stretch of coastline can experience the event in completely different ways. One might see a sudden vertical wall, the other a silent surging flood, and both can be equally deadly. Even the same tsunami can behave differently as it travels. When the wave hits a small island, it might wrap around it and converge on the far side, doubling its strength. In narrow harbors, it might bounce back and forth, creating chaotic waves that build on each other. It's not a single clean strike, it's a system in motion, one that changes shape depending on every obstacle, every dip, and every angle it encounters. This is why survivors often describe scenes that seem completely different from one another. Some recall a thunderous wall crashing down like a building. Others describe a sudden rush of water that arrived without a sound. The truth is, they're both right. Tsunamis are shaped by what's beneath and around them, and they respond with terrifying precision to the contours of the earth. It's this ability to change form that makes tsunamis especially deceptive. They can arrive looking calm and rise into chaos. They can start as gentle swells and end as crashing monsters. And because they don't always follow the visual cues we're used to, the cresting of a wave, the roar of surf, they can lull people into a false sense of safety. But regardless of what form they take, the energy inside them is the same. It is relentless, reshaping itself to match the shore it strikes. And as that energy continues pushing forward, carving paths through roads, forests, and buildings, it's not done shifting shape yet, because the next part of the story isn't just about water anymore, it's about what's caught inside it and how that transforms the tsunami from a flood into a weapon. As the tsunami approaches the shore, the shape it takes and the damage it causes aren't determined by water alone, but by what lies hidden beneath it. The ocean floor, though unseen by the eye, acts like a sculptor. It can stretch, bend, split, or concentrate a wave, quietly deciding whether a coastline will be spared or shattered. The topography of the seafloor, the mountains, valleys, ridges, and canyons beneath the waves, plays one of the most critical roles in the final moments before impact. Imagine the bottom of the ocean not as flat, but as a vast underwater landscape. There are enormous seamounts, essentially underwater volcanoes that rise like giant hills from the deep. There are long ridges that snake across the ocean like submerged mountain chains. There are deep yawning trenches that run like scars along the sea floor, sometimes deeper than Mount Everest is tall. These features don't just sit passively below the surface. They interfere with tsunami waves as they pass, redirecting their energy in powerful and unexpected ways. When a tsunami travels across the open ocean, it spreads out in all directions like ripples in a pond. But once those ripples encounter underwater features, everything begins to change. A seamount might slow down one part of the wave, while the rest continues moving at full speed. That imbalance can cause the wave to twist and compress, concentrating its energy into a narrower path. This process is similar to how a magnifying glass focuses light into a hot point, except here, it's water being focused into a violent surge. These natural focusing points are sometimes called wave lenses. They don't just bend the wave, they amplify it. And the areas where those focused waves make landfall often experience much more destruction than neighboring regions. Two towns along the same coastline might be only a few miles apart. One might see ankle deep flooding, the other might be completely flattened, all because of the invisible shapes far beneath the sea. It's not always a matter of size. Even small underwater features can have large effects if they're positioned just right. A shallow ridge might lift the wave ever so slightly, just enough to give it more height when it finally reaches land. A narrow trench might cause the wave to stretch sideways, pulling its energy out across a broader area. Sometimes these effects cancel out, softening the blow, but other times they stack together and send all the energy hurtling toward one unlucky stretch of coast. Computer models have helped scientists visualize these effects more clearly. Using real world data about seafloor topography, researchers can now simulate how a tsunami would move through different underwater landscapes. In these simulations, you can watch as the wave starts out as a smooth circular ring, but as it encounters trenches, ridges, and slopes, it begins to warp. One side surges forward, another slows down. The once even wave becomes jagged, funnel shaped, and unpredictable. These distortions don't just change how the wave moves, they change when it strikes. In some places, the tsunami might arrive minutes earlier than expected. In others, the wave might appear to pause, only to return stronger and faster. The timing becomes erratic, and this unpredictability makes early warning systems even more difficult to manage. You can't rely on simple distance or direction alone. You have to know exactly what's on the ocean floor between the origin and the coast. Even after the wave reaches land, its behavior can still be affected by underwater topography just offshore. If the coastline is fronted by a steep drop, the energy may stay more focused and explosive. If it's protected by an offshore reef or series of underwater ridges, some of the wave's power might be absorbed or redirected. These protective features can sometimes act like natural shields, but they're not perfect, and they don't work the same way for every event. One of the most startling examples of this can be seen in the aftermath of the 2004 Indian Ocean tsunami. Some areas that were expected to be devastated experienced minimal damage. Others, thought to be out of the direct path, were overwhelmed. Later analysis showed that underwater ridges and trenches had redirected the energy in surprising ways, focusing the full force on small regions while skipping over others entirely. This hidden influence of the seafloor reminds us how complex the mechanics of a tsunami really are. The wave you see rising at the shoreline is only the final shape, molded by everything it's passed over since it began. It's not just water that dictates its power, it's the unseen terrain stretching thousands of kilometers beneath it, shaping the energy silently from below. And this reshaping doesn't stop once the wave crashes into land, because after that first impact, something strange begins to happen. The water doesn't just recede quietly. In many cases, it turns around and begins to bounce back, reflecting off coastlines and echoing across the ocean in waves that are far from finished. What makes tsunamis even more terrifying is that the first wave often isn't the last. In fact, it's rarely the strongest. After the initial surge crashes onto land, many people think the danger has passed. But beneath the surface, the ocean isn't finished. A tsunami is not just a single wall of water, it's more like a series of waves traveling together, one after another, like a train crossing the sea. This phenomenon is called a wave train, after a major underwater disturbance like an earthquake or a landslide. The displaced water doesn't just form one pulse and then stop. It sends out a sequence of pulses, each traveling through the ocean with its own timing, shape, and intensity. These waves are separated by long gaps, sometimes 10 minutes apart, sometimes even over an hour. And that long pause between waves can be dangerously misleading. When the first wave hits and then the water recedes, there's a strong urge to assume the worst is over. People may come out of hiding. Emergency responders might start assessing damage. Some may even begin cleanup efforts, thinking they've survived the full force. But this is when the second or third wave can strike, often stronger than the first, catching people off guard and making an already devastating event even more deadly. The wave train doesn't behave like normal ocean waves that come in regular patterns. Each wave in a tsunami train is shaped by the original energy source, the seafloor it passes over, and how it reflects off coastlines. That means one wave might crash inland with massive power, while the next rolls in more gently. Then suddenly, the following wave arrives with renewed, unexpected force. This unpredictable rhythm is part of what makes tsunamis so destructive. Unlike the rhythmic ebb and flow of tides, tsunami wave trains create chaos. Some waves crash with extreme energy and flood far inland. Others might appear smaller, but still carry enough force to destroy buildings, sweep away vehicles, and drag people into the current. These waves can strike repeatedly, grinding down what was left standing after the last. In the 2011 Japan tsunami, for example, the first wave devastated the coastline, but the second and third waves overwhelmed inland areas, breaking through barriers that had barely survived the initial strike. The sequence of waves didn't give people a chance to recover. Each new arrival tore through weakened structures and brought even more debris and water inland. By the time the wave train ended, entire towns were gone. Even more unsettling is that these waves can continue for hours. Depending on the size and shape of the ocean basin, a tsunami wave train can stretch out over an entire day, with waves rebounding across vast distances and returning again. A single quake in one region of the world can generate a chain of waves that ricochet off distant coastlines, loop back across the ocean, and hit places that thought they were in the clear. The psychological toll this takes is immense. People already overwhelmed by the first strike are left in a state of fear, waiting and watching for what comes next. With every lull in the water, there's anxiety. Is it truly over, or is another wave on its way? Survivors often describe the fear of not knowing when the next hit will come and whether they'll be able to outrun it. Some say the silence between waves is worse than the waves themselves. This cycle of destruction in phases also complicates rescue efforts. Emergency teams can't safely enter the danger zone right after the first wave because they know more are likely coming. Helicopters, boats, and ambulances may be forced to wait, knowing that people are stranded or injured just beyond reach. The rhythm of the wave train turns every second into a gamble, both for survivors and responders. And there's another hidden risk. Debris left behind by the first wave becomes a hazard when the next one hits. Flooded cars, pieces of homes, downed power lines, all of it can be picked up and slammed again and again by each wave in the train. What began as scattered wreckage becomes a churning soup of destruction, pushed farther inland with every pulse. The pattern isn't always obvious, and without real time monitoring systems, coastal communities may not know how many waves to expect or how far apart they'll be. This is why warnings often stay in place for many hours after the first wave hits. The ocean may look calm, the sky may clear, but the wave train could still be underway, and the most powerful surge may yet be approaching. As the waves continue to travel, they also reflect and refract off coastlines and undersea features, creating complex interference patterns. In some cases, smaller waves combine to create a larger one, a process called constructive interference. It's like two voices shouting in sync, making the impact even louder. These amplified waves can appear suddenly and carry more power than anyone expected, even late into the sequence. And all of this is happening while the ocean continues to shift beneath our feet. Each wave in the train carries not just water, but a memory of the forces that created it, and it delivers that memory to every shore it touches. But the wave train doesn't just end with impact. Sometimes what comes next is even stranger. The way the ocean reflects those waves back again, like echoes repeating a terrible event across the globe. To understand the danger tsunamis pose, it helps to compare them with other familiar forces of the sea, like tides and storm surges. On the surface, they might seem similar. After all three involve large amounts of water pushing onto land. But beneath that surface, their origins and behaviors couldn't be more different. Mistaking one for the other could cost lives, which is why it's so important to understand the differences. Let's start with tides. These are slow, predictable rises and falls of the ocean's surface caused by the gravitational pull of the moon and to a lesser extent the sun. They happen every day in a steady rhythm, and they're so regular that tide tables can predict them years in advance. High tide, low tide, the cycle continues, gently moving water inland and back out. People living on the coast are used to this rhythm. Tides don't rush in suddenly, they're gradual, and while they can cause flooding during a full moon or king tide, they rarely catch anyone by surprise. Storm surges, on the other hand, are pushed by wind. When powerful storms like hurricanes or cyclones move over the ocean, their strong winds press down on the water's surface and shove massive amounts of water toward the shore. This creates a dome of elevated sea level that can spill over coastlines, especially during high tide. Storm surges are dangerous. Yes, they can flood cities, smash buildings, and sweep away vehicles, but they usually come with plenty of warning. Meteorologists track hurricanes days in advance. People can evacuate. Governments can prepare. Tsunamis are different. They don't rely on wind or the moon. They're triggered by sudden violent shifts in the Earth's crust, a rupture deep below the ocean, or a massive underwater landslide, or a volcanic collapse. And once that energy is released into the water, it creates a wave with a completely different behavior. Unlike tides and surges, a tsunami doesn't just lift the surface of the water, it moves the entire water column, from the surface all the way down to the seafloor. That's why it carries so much energy. It's not just a surface ripple being pushed around by air, it's the ocean itself being shoved by Earth's own shifting plates. This gives tsunamis a speed and force that other coastal floods simply can't match. Another major difference lies in how these waves behave as they move inland. A tide might creep in gently and retreat. A storm surge may spill over seawalls, rise quickly, and then drain out. But a tsunami doesn't behave like either. It's often a massive continuous surge of water that keeps going, sometimes for miles inland. It doesn't stop where the beach ends. It moves across roads, climbs hills, and crashes through towns like a liquid bulldozer. This is why tsunami warning systems can't just rely on the same tools used for tides or storm tracking. Tidal gauges and storm radar look at surface level conditions, wind speed, air pressure, water height. But tsunamis are deep water events. Their most telling signs happen miles offshore and far beneath the surface, which is why specialized sensors are needed. Instruments like dart buoys and deep sea pressure sensors are designed to detect the small but sudden changes in ocean pressure that signal a tsunami wave is coming. Traditional tide monitors wouldn't even notice. The warning time is another stark contrast. Storm surges give us hours or even days of notice. Tsunamis often give minutes. In some cases, especially near the earthquake's epicenter, people have only seconds before the wave arrives. There's no dark sky or howling wind to tip people off. The ocean might look strangely calm until it rushes back or surges forward without warning. And while storm surges often lose power as they push inland, meeting resistance from land, buildings, and gravity, tsunamis tend to do the opposite. As they hit shallow water, their height increases, their speed drops, but the water piles up, becoming taller, stronger, and more forceful. That's why a tsunami that looked harmless in the open sea can become a 10 or 20-meter wall when it reaches the coast. It's also important to remember how far inland a tsunami can go. Tides might flood a beach, storm surges might push a few blocks into a city, but a tsunami can plow through entire towns, pushing water 2, 3, or even more kilometers inland. In the 2004 Indian Ocean tsunami, waves traveled as far as 5 kilometers inland in some places, leaving a trail of destruction well beyond the coastline. Traditional flood maps didn't account for that kind of reach, and many people living just outside the flood zone were caught off guard. This is why tsunami maps are drawn differently. They don't just mark the usual flood prone zones, they model worst case scenarios based on seafloor topography, elevation, and potential wave amplification. In places like Japan and Chile, where tsunami risk is high, you'll see tall evacuation signs even in inland neighborhoods. Because when the water comes, it comes hard and it comes far. These differences are not just academic, they shape how we prepare. A community ready for high tides or even hurricanes may still be completely unprepared for a tsunami. The behavior, the speed, the energy, the inland reach, all of it requires a different mindset, one that understands the ocean not just as something we see on the surface, but as a body of hidden power that can change in an instant. And while we've built systems to track tides and monitor storms, understanding how tsunamis move is still evolving. Scientists are learning more about what shapes their journey, what amplifies their energy, and what makes them so unpredictable. And just as important as how they start is where they go next. As the towering wall of water approaches the shore, another force begins to act on it, one that isn't always obvious, but plays a massive role in what happens next. It's the ground beneath the wave. The interaction between the rushing water and the seafloor, especially as the tsunami moves from deep water to dry land, begins to change everything. This is where friction enters the picture. In the deep ocean, a tsunami moves swiftly and smoothly. There's very little resistance because the water is deep and the wave energy is spread through the entire vertical column from the surface to the seafloor. But as the tsunami gets closer to land, the water becomes shallower, and that changes the game entirely. The bottom of the wave starts scraping against the ocean floor. It's like slamming the brakes on a speeding train, but only on the lower part of the train while the top keeps going. The result? The wave slows down, but it doesn't lose power. That energy has to go somewhere. And so instead of moving forward quickly, the wave starts rising. Its speed drops, but its height builds. The force that once carried the wave horizontally now lifts it vertically. This is why tsunamis that may have been only a meter high in the deep sea can suddenly stand 10 meters tall or more as they reach the shore. It's not magic, it's physics. The energy is being squeezed into a smaller and smaller space. And since water can't compress like air can, it has no choice but to rise. The shape of the coastline plays a huge part in how dramatic this transformation becomes. Think of a steep coast like a rocky cliff that drops sharply into the sea. When a tsunami hits a coast like that, the water doesn't have much shallow space to interact with. The wave slams into the cliff and releases its energy in a concentrated burst, but it doesn't have time or space to build height gradually. These areas might get hit hard and fast, but the flooding typically doesn't move very far inland. Now contrast that with a flat, wide coastal plain, places where the land stretches out almost level with the ocean, beaches, deltas, or low-lying coastal farms. Here, the tsunami behaves very differently. As it moves into the gradually shallowing water, it slows down bit by bit. But that slowing spreads across a wider distance, giving the wave more time to rise, more space to expand, and more area to flood. This is where friction and coastal drag become deadly. As the bottom of the wave continues to interact with the land, the roughness of the seabed, sand, vegetation, and even man-made structures all contribute to the drag. The water doesn't just slide in smoothly, it gets caught, slowed, and redirected. But instead of stopping the wave, this process adds turbulence and volume. Water gets backed up behind the slowing front, piling higher. The more resistance the bottom of the wave feels, the taller it can become. The tsunami starts to act less like a wave and more like a rolling flood that doesn't stop until the landscape itself finally interrupts it. In many cases, the most catastrophic tsunamis occur in places with shallow continental shelves, wide stretches of ocean floor that slope gently upward before hitting land. These shelves give the tsunami time to build in size and intensity, creating massive walls of water that aren't just tall but heavy and wide. And because there's no sudden elevation change to block the water, the flood can travel miles inland, destroying everything in its path. You can think of it like pouring water into a funnel. If the funnel is narrow and steep, the water shoots straight through. But if the funnel is wide and shallow, The water spreads out and slows, but also builds up, pressing outward as it moves forward. That's the danger with flatter coasts. The water doesn't stop quickly, and there's nothing to contain it. Even the materials on the coast matter. Soft, sandy terrain offers less resistance than rocky ground. Urban areas with streets, walls, and buildings can both slow the wave and trap it, causing water to surge around obstacles, rebound off structures, and flow unpredictably. In some towns, this has led to wave height increasing in narrow streets where water has nowhere else to go, channeling the surge into concentrated rivers of destruction. Coastal vegetation like mangroves or dense forests can provide some resistance. Their tangled roots and thick canopies absorb a small part of the wave's energy and slow the flow. In parts of Southeast Asia, villages with intact mangrove belts suffered less damage than those where trees had been cleared. But even then, the protection only goes so far. When a wave carries the force of an entire ocean, even forests can be flattened. As the tsunami continues to push inland, it's not just the height that matters anymore. It's the volume, the mass of water behind that leading edge, carrying debris, pressure, and weight. The longer the slope, the more time the wave has to drag itself forward, overwhelming fields, houses, and roads with sheer momentum. What starts as a single wave becomes a churning inland flood, surging past what most people thought was a safe distance from the sea. And yet, even after the wave has rolled through, the damage isn't done. The water doesn't just stop and vanish, it lingers. It fills buildings, it pulls back with terrifying strength, dragging cars, trees, and people with it. And in many cases, it sets the stage for more waves to come, each one shaped by the land it moves across and by the silent, invisible hand of friction beneath its surface. As the wave charges inland, dragging with it the weight of the sea, its transformation is no longer just about height or speed. It becomes about raw, unfiltered force. This is the moment when the ocean stops acting like water and starts behaving like a moving wall of destruction. It doesn't gently rise or quietly seep into the streets, it bulldozes. Tsunamis carry far more than just water. Unlike wind driven waves, which may crash and recede, a tsunami is a sustained push, thick with momentum, layered with energy from ocean surface to seabed, and dense with debris picked up along the way. It doesn't merely flood a place, it rips it apart. Anything in its path, houses, power lines, trees, cars, bridges, is no longer anchored, no longer safe. The tsunami doesn't discriminate. If it can move it, it will. The forces involved are beyond what most buildings or infrastructure are designed to withstand. Imagine a single cubic meter of water, it weighs about a ton. Now multiply that by thousands, all packed together and moving at high speed. That's the weight behind the first wave. And it's not just the water itself, it's everything the wave has scooped up: logs, sheet metal, glass, buses, rebar, entire walls. The ocean becomes a moving junkyard, a massive battering ram. In coastal forests, centuries old trees, some with roots buried deep into the earth, are ripped from the soil like weeds. Concrete roads buckle under the weight. Shipping containers are thrown inland like dice, and steel beams, designed to flex under hurricane force winds, bend like paper clips. The power isn't just in the push, it's in the unrelenting volume, a massive surge that doesn't stop until friction and distance finally bring it to a crawl. Footage from real disasters reveals the true violence of this force. During the 2011 tsunami in Japan, entire neighborhoods disappeared in minutes. Multi-story buildings crumbled as water rushed through them. Cars were lifted from highways and floated off like driftwood. In one haunting clip, the camera captures the exact moment a seawall is breached. once thought to be an impenetrable barrier, and the ocean surges over it as if it were never there. What followed was a roar of breaking timber, twisting metal, and unstoppable water. Another video from Banda Aceh in the 2004 Indian Ocean tsunami shows the waves swallowing a mosque, tearing through walls and windows before hurling furniture and people into the current. Rescue workers later found reinforced concrete pillars that had been cracked and split clean through. In ports and shipyards, vessels weighing thousands of tons were hurled inland, crushing buildings as they went. One large cargo ship in Sri Lanka ended up in the center of a small village, dry docked by the wave itself. This kind of damage doesn't happen because the water is especially fast. By the time it reaches land, it may only be moving 30 to 50 kilometers per hour. What makes it lethal is the mass. There's simply too much of it to resist. When that much water moves, it carries the kinetic energy of a jetliner, and it's not flying over your house, it's flying through it. What's even more alarming is how quickly this destruction can unfold. From the moment the wave hits the shore to the time it reaches the inland edge of its reach, only a few minutes may pass. Within that short window, entire lives are upended. Bridges snap, electrical substations explode. Schools and hospitals, once considered safe zones, are flooded and crushed. The built environment is no match for an angry ocean. And while buildings can be rebuilt, roads repaved, and power lines restored, what lingers is the evidence of violence etched into everything left behind. Streets become rivers choked with broken glass and shattered bricks. Parks turn into fields of twisted cars and household debris. A playground swing set bent in half, a mattress wrapped around a telephone pole. The ordinary is transformed into a museum of catastrophe. Even the ground itself bears scars. In Japan, entire fields were scoured clean, stripped of topsoil, and replaced with saltwater pools. In Alaska, after the 1958 Lituya Bay mega-tsunami, trees were flattened over 500 meters up a mountainside, marking a line as if painted by a giant's hand. It's a kind of destruction that rewrites the landscape, leaving no question of what passed through. As the wave finally slows, not because it wants to, but because the terrain takes its toll, the destruction doesn't end. The remaining energy finds new ways to wreak havoc, pulling structures apart from the inside, lifting foundations, crumbling basements. Even as the water recedes, it tears back what it brought forward. And in that moment, the full power of a tsunami becomes clear. It's not just a force of water, it's a battering ram powered by gravity, speed, and scale. And once it's set in motion, almost nothing can stop it. And just as the sea starts to withdraw, leaving behind a broken world, another silent danger is taking shape in its wake. As the tsunami sweeps further inland, the water itself is no longer the only threat. In fact, the true danger begins to multiply with every second that passes. What starts as a massive surge of ocean turns into a chaotic river of destruction, and it's not just water rushing forward. Everything caught in the wave is now part of the weapon. Trees, cars, boats, rooftops, chunks of concrete, entire walls, and shattered pieces of homes and stores all begin to float, collide, and accelerate. What was once part of a neighborhood quickly becomes high speed debris, and that's when the tsunami becomes even more deadly. At first, this debris drifts, spinning slowly in the rising flood. But as the wave picks up force and moves across roads, rivers, and city blocks, the objects in its path are pulled into motion. Some float at odd angles, barely above the surface. Others tumble end over end. The speed builds quickly, and before long, these seemingly ordinary items become lethal. A tree branch turns into a spear, a car becomes a rolling battering ram, a sheet of metal transforms into a blade. The physics are brutal and simple. Anything the wave touches becomes a projectile. Kinetic energy, the energy of motion, is what turns this debris into shrapnel. The faster an object moves, and the heavier it is, the more destructive it becomes. That's why a slow moving wave that carries a heavy truck can do more damage than a fast wave carrying only water. Picture a large steel beam lifted by the wave and hurled sideways through a house. It doesn't just break a wall, it slices through everything in its path. A motorcycle floating downstream may be carried for hundreds of meters before crashing through a storefront at high speed. A piece of furniture might smash through a window, trapping people inside. This secondary destruction often causes more fatalities than the initial wall of water. People who survive the first surge by climbing to higher ground or sheltering inside a structure are still at risk from the violent chaos of debris slamming into buildings or being thrown through the air. Survivors have reported watching entire vehicles crash through the second floors of homes. Others describe walls suddenly exploding inward as logs or dumpsters punch through with unstoppable force. In the 2011 tsunami that struck Japan, entire fishing boats were lifted onto rooftops. One video captured a house being pushed sideways by the wave, only to be completely destroyed when it collided with a second home being carried behind it. The collision sent splinters, glass, and metal flying in every direction. Emergency crews later found the remains of buildings compressed into single, tangled piles, cars wrapped around staircases, bicycles fused into crumpled fences, and power poles snapped like toothpicks. And this chaos isn't just limited to the wave's initial landfall. As the water moves further inland and winds through cities, the debris follows, collecting more pieces along the way. What starts as a tree can become a debris chain, snagging a fence, a chair, a gas tank, a trash bin, and then a motorcycle, all moving as one tangled, deadly mass. Each object adds to the danger, not just in size, but in speed. And since water resists slowing down, everything caught inside keeps moving, breaking through anything in its path. What makes this even more terrifying is how unpredictable it becomes. One neighborhood might be completely destroyed, while the one beside it is barely touched, simply because the path of debris shifted by a few meters. A single shipping container, once docked safely at a port, can turn into a missile traveling several blocks inland, crushing everything in its way. And because these objects aren't smooth or uniform, they often tear through infrastructure in unexpected ways, catching on corners, jamming into doors, or collapsing stairwells. Even after the wave begins to recede, the danger doesn't go away. All that debris, now scattered across roads and neighborhoods, becomes a deadly obstacle during rescue efforts. Broken glass, live electrical wires, unstable structures, and sharp metal fragments litter the area. And worse still, the retreating waters can drag debris back out to sea, creating a reverse pull that's just as destructive. Survivors have recounted how large appliances were suddenly yanked out of buildings and swept away. Others saw entire cars that had floated inland be dragged back into the ocean, rolling and flipping as they went. This back and forth movement, first in, then out, means the debris becomes a recurring threat. The same object that hit a building once can return minutes later, striking again from a different direction. For those trying to flee or hide, there's no predictable safe zone. Anything that floats, rolls, or can be lifted is a risk. And with each new wave in a tsunami train, the cycle of destruction repeats. More debris, more damage, more risk. As the ocean recycles its fury, the landscape becomes a battlefield of twisted steel and shattered lives, setting the stage for yet another layer of the tsunami's terrifying complexity. Once the wave has torn through its first coastline, it doesn't simply vanish. The ocean doesn't absorb the energy like a sponge. Instead, the wave keeps moving, but now it starts bouncing, much like an echo bouncing off the walls of a canyon. Tsunamis can reflect and rebound, not just once, but multiple times, traveling across entire oceans and ricocheting off distant land masses. This effect turns a single tsunami event into a worldwide ripple, with waves continuing to circle the globe long after the initial trigger. When a tsunami wave slams into a coastline, not all of its energy is used up in flooding or destruction. A portion of that energy is reflected back into the ocean. This rebounding water forms secondary waves that move in the opposite direction, back out to sea, away from the coast. These reflected waves aren't always smaller or less dangerous. In some cases, they can combine with other waves traveling through the ocean and gain strength again, forming new fronts of energy that head toward completely different shorelines. The shape of the seafloor plays a huge role in this process. If a coastline is curved or steep, it can act like a mirror focusing the rebound in a specific direction rather than scattering it. Imagine a giant stone thrown into a massive, oddly shaped bowl. The ripples don't spread evenly. Instead, they curl, bend, and ricochet along the edges, bouncing again and again in specific paths. That's exactly what happens with tsunami reflections on a planetary scale. Underwater ridges, continental slopes, and island chains help guide these echoes across thousands of kilometers. And they travel fast. Even after being reflected, tsunami waves can still maintain speeds of several hundred kilometers per hour in the deep ocean. That means a wave that initially hits the coast of South America can reach Southeast Asia or the Pacific Islands in just over a day. These aren't just theoretical risks, they're real, measurable, and historically documented. One of the most dramatic examples comes from the massive earthquake off the coast of Chile in 1960. It was the most powerful earthquake ever recorded, a magnitude 9.5, and the tsunami it generated didn't just devastate Chile's coastline, it traveled over 17,000 kilometers across the Pacific Ocean and struck the shores of Japan more than 22 hours later. The waves that arrived weren't aftershocks, they were echoes, rebounding across the sea, having ricocheted off other coastlines, deflected by the curvature of the earth and the underwater terrain. In Japan, those tsunami echoes from the Chilean quake still caused deadly damage. Buildings were destroyed, seawalls were breached, and lives were lost. Despite the incredible distance and the time that had passed, the power of the rebounding waves was enough to cause significant destruction. These weren't remnants, they were full blown waves that had simply taken the long way around. The same pattern was observed during the 2004 Indian Ocean tsunami. After slamming into coastlines across Southeast Asia, the wave didn't simply stop. Reflections were recorded traveling around the globe multiple times. In fact, some of the later waves that hit the east coast of Africa, thousands of kilometers from the quake's epicenter, were a combination of initial waves and their rebounded counterparts, merging, reinforcing, and delivering a second punch to places that thought the worst had passed. This lingering threat is why tsunami warnings aren't always canceled quickly. In some cases, scientists continue to monitor coastlines for many hours, even days after the initial wave. The reflected waves can return with unexpected strength, often catching people off guard. Just because the first wave is over doesn't mean it's safe. In fact, it may only be the beginning of a longer, more complex series of impacts. What makes this even more complicated is how these echoes interact with one another. When two reflected waves cross paths, they can interfere with each other, either canceling each other out or reinforcing their energy. This is known as wave interference. In the best case scenario, the waves overlap in a way that weakens them. But in the worst case scenario, their energies combine, a phenomenon called constructive interference, forming a larger, more powerful wave than either would have been alone. All of this means that a tsunami isn't a single event, it's a network of shifting forces that move and morph as they circle the planet. And while we can measure and model some of these interactions, many of them are still hard to predict with perfect accuracy. One reflected wave may pass harmlessly through open ocean, another may find a channel, bend around an island chain, and crash into an unexpected part of the world with devastating strength. As these echoes continue to ripple outward, they add to the complexity of any tsunami response. Each coastline must be treated not just as a destination, but as a potential origin point for further waves. The ocean, in this way, becomes a chamber of echoes, never truly still, always capable of bouncing one last wave toward a distant shore. When the ground shakes beneath the ocean and a tsunami is born, it becomes more than just a wave. It becomes a marker in history. Some tsunamis have struck with such power and consequence that they've reshaped coastlines, rewritten safety codes, and haunted the collective memory of entire nations. Among the most devastating in modern times was the 2004 Indian Ocean tsunami, a single event that revealed the terrifying scale of what these waves can do. On December 26, 2004, an undersea earthquake struck off the west coast of northern Sumatra. It was a magnitude 9.1, 9.3 quake, making it one of the most powerful ever recorded. But it wasn't the shaking alone that caused disaster, it was what followed. The seafloor abruptly shifted, pushing up a massive column of water that spread outward in all directions. In the open ocean, ships barely noticed the change. But when the waves reached land, they rose into monstrous walls and swept across coastal towns with no mercy. What made this tsunami especially catastrophic wasn't just its power, it was its reach. Waves struck Indonesia, Thailand, Sri Lanka, India, and even parts of East Africa. In some places, the water surged several kilometers inland, flattening villages, tearing buildings from their foundations, and pulling people into the sea. There was no widespread warning system in place at the time. Many people had never even heard of a tsunami. They didn't know what the retreating water meant. By the time they realized something was wrong, it was too late. In total, more than 230,000 people across 14 countries lost their lives. Entire communities vanished in minutes. The scale of destruction was overwhelming, not just in terms of lives lost, but in homes destroyed, families separated, and infrastructure wiped out. The Indian Ocean tsunami became the deadliest tsunami in recorded history, and it exposed how unprepared much of the world was for something of that magnitude. That tragedy led to a global effort to improve tsunami detection and response systems, especially in the Indian Ocean region. But less than a decade later, another disaster reminded the world that even high tech nations aren't immune to the chaos of the sea. In March 2011, Japan experienced a magnitude 9.0 earthquake off its northeastern coast. The quake itself was devastating, but again, it was the wave that followed that did the most damage. The tsunami that rose out of the Pacific traveled quickly and with immense force, striking Japan's Tohoku region just minutes after the quake. In some places, the water surged over seawalls, swept past warning sirens, and drowned entire cities. One of the most haunting images from that day came from the Fukushima Daiichi nuclear power plant. The tsunami overwhelmed its protective barriers, flooded the backup power systems, and triggered a nuclear meltdown. Explosions rocked the facility, radioactive materials leaked into the environment, and thousands had to be evacuated. It wasn't just a natural disaster anymore, it had become a nuclear one. That single tsunami exposed vulnerabilities not only in infrastructure, but in assumptions about what nature could throw at us. Japan's preparedness and technology likely saved many lives that day, but even the best planning couldn't fully protect against the sheer scale of the wave. Over 15,000 people died, and many more were displaced. Entire neighborhoods became fields of rubble, and the psychological toll from both the tsunami and the nuclear disaster still lingers in the country's collective memory. But even these modern events are only part of the story. Long before modern records, tsunamis left their marks in places we wouldn't expect, like the forests of Alaska. In 1958, a massive landslide fell into Lituya Bay after an earthquake shook the region. The sudden collapse of rock into the narrow inlet displaced so much water that a wave nearly 525 meters tall surged up the surrounding slopes. Trees were snapped off halfway up the cliffs, and the wave swept two fishermen and their boat completely out of the bay. Though only a few lives were lost due to the remote location, this event holds the record for the tallest tsunami wave ever recorded, a so-called mega-tsunami. Unlike regular tsunamis caused by tectonic shifts, this one was triggered by a sudden rockfall. The sheer size of the wave shows what's possible when huge masses of earth plunge into confined water bodies. Lituya Bay became a case study in the raw potential energy stored in gravity and geology, revealing that not all tsunamis need a massive earthquake to form. Sometimes a falling mountain is enough. These events, while separated by geography and time, share a common thread. They demonstrate how the sea, normally a symbol of calm or commerce, can turn into a force of unimaginable destruction. And the more we understand about these famous tsunamis, the better we can prepare for those that may still come, because the ocean never forgets, and history shows it will strike again. Not all tsunamis begin with shaking ground or sliding plates. Some are born in silence until the collapse, the crash, or the impact arrives. In parts of the world where ice clings to cliffs and ancient glaciers creep toward the sea, there lies a different kind of danger. When a glacier collapses, it can unleash an enormous wall of water, especially if it plunges suddenly into a fjord or enclosed bay. These cold-born waves can rise quickly and travel with terrifying speed, catching coastal villages off guard. In Greenland and parts of Alaska, scientists have documented instances where retreating glaciers fractured and sent millions of tons of ice into the ocean in a matter of seconds. That impact acts much like a rock thrown into a pool, except on a scale that defies imagination. The splash becomes a surge, and the surge becomes a localized tsunami. Entire fishing communities, cabins, and boats can be swept away in moments. These glacial collapse tsunamis are rare, but as the planet warms and ice sheets continue to melt, the risk grows. Coastal settlements near glaciers now face not only the slow rise of sea levels, but also the sudden threat of wave generated devastation. But if ice can trigger a tsunami, so can fire, or rather, what falls from the fire above. Meteor impacts represent one of the most extreme causes of oceanic tsunamis. When a space rock, large enough and fast enough, slams into the sea, The result isn't just a splash, it's a colossal explosion. The shock wave radiates outward, displacing vast volumes of water in all directions. It doesn't take long for this displaced mass to form a tsunami, one that can circle the globe more than once, gaining height as it slams into coastlines. Imagine a meteor the size of a city block hurtling toward Earth at tens of kilometers per second. When it hits the ocean, the blast vaporizes water instantly, throws debris into the atmosphere, and pushes outward a wave hundreds of meters tall. These aren't just tsunamis, they're extinction level events. Many scientists believe that the asteroid that wiped out the dinosaurs 66 million years ago didn't just trigger wildfires and a global winter. It also sent mega-tsunamis racing across prehistoric oceans, drowning entire ecosystems and coastal habitats in its wake. The idea of an apocalyptic scale tsunami isn't science fiction, it's buried in our planet's history. Sediment layers in some coastal regions show signs of massive ancient waves, taller than any seen in modern times, possibly triggered by asteroid impacts or enormous landslides. These waves were not just high, but long lasting, carving and reshaping coastlines in a matter of hours. They arrived not as one blow, but in pulses, giant wave trains of destruction that rewrote the geography of the continents. But what if we looked beyond Earth? On the red planet, there's mounting evidence that Mars may have once experienced something very similar. Satellite imagery has revealed vast flat areas that resemble dried seabeds, along with strange flow patterns that mimic tsunami run ups on Earth. Some scientists now propose that billions of years ago, when Mars had liquid water and possibly oceans, it may have been struck by massive asteroids that sent Martian tsunamis sweeping across its surface. These waves would have been frozen quickly by the cold Martian climate, leaving behind icy scars and rippling landscapes still visible today. Unlike Earth's tsunamis, which roll through dense oceans and climb inland with unstoppable force, a Martian tsunami would have behaved differently. The atmosphere is thin, the gravity weaker, and the temperatures brutally cold. Yet the physics is still the same. A sudden impact into a body of water releases energy. The water moves outward, fast and high. On Mars, that wave may have frozen mid flow, preserving a geological snapshot of catastrophe. These fire and ice tsunamis, born from collapsing glaciers, falling meteors, and ancient alien oceans, expand the story of tsunami science far beyond what happens along fault lines. They show that under the right conditions, the forces capable of displacing oceans can come from above or from the melt of ancient ice. Some leave no survivors, others leave only questions carved into rock. But all serve as a stark reminder it isn't only what lies beneath the sea that we need to watch. Sometimes the greatest waves come from the sky or from the melting heights of ice that once seemed eternal. And as we continue to study the deep past and look to other worlds, the blueprint for these colossal waves helps shape our understanding of what the planet and perhaps others have endured. Whether triggered by a crumbling glacier or a fireball from the heavens, the story of the tsunami is never just a local one, it's planetary, and it's still unfolding. Deep beneath the ocean's surface, long before the water begins to rise along distant shorelines, an invisible network is already listening. These are the sentinels of the sea, pressure sensors, underwater microphones, and floating buoys designed not to prevent disaster, but to see it coming just early enough to warn those in its path. Modern tsunami detection starts with one crucial question: how do you know something is coming when there's nothing to see? In the open ocean, tsunamis don't form towering waves. They can pass silently under ships without notice. So scientists don't look for the wave itself, they watch for the energy moving through the water. That's where the DART system comes in, short for Deep Ocean Assessment and Reporting of Tsunamis. It's a global network of sensors and buoys that monitor pressure changes at the bottom of the sea. Each DART station is made of two parts, a seafloor pressure sensor and a surface buoy. The sensor, anchored to the ocean floor thousands of meters below, detects tiny changes in the weight of the water column above it. When a tsunami begins to pass overhead, even a subtle rise in pressure is recorded. That signal is then sent up to the buoy floating on the surface, which relays the data via satellite to monitoring stations on land. From there, computers crunch the numbers to determine whether a tsunami is forming and how fast it's traveling, how high it might be, and where it's likely to go. This pressure based method is incredibly sensitive. A dart buoy can detect a change in sea level as small as a centimeter, even in water that's more than 3 miles deep. That's how scientists can spot the early signs of a tsunami long before it reaches any coastline. The speed of this detection is vital because once a tsunami is in motion, every second matters. But pressure readings alone don't tell the whole story. That's why DART buoys are supported by other systems, including seismic sensors and hydroacoustic monitors. When an earthquake strikes beneath the ocean floor, seismic stations instantly register the shaking. This data can give a rough estimate of the quake's strength and location, which helps scientists determine whether the conditions for a tsunami have been met. But seismic activity doesn't always result in a tsunami. That's where hydroacoustic sensors come in. These devices listen for underwater sounds, like the groan of shifting rock or the sudden slide of a submarine landslide. They're especially useful in identifying events that may not show up strongly on seismographs, but still have the potential to displace massive volumes of water. Together, these systems form a multi layered safety net, not one single point of failure, but a coordinated grid of eyes and ears tuned to the movements of Earth itself. And once the signals are gathered, it becomes a race against time. Computers run predictive models, simulating wave speed and impact zones. Emergency agencies issue alerts. Sirens sound in coastal villages. Evacuation plans activate. In some cases, the warning window is generous, an hour, maybe two, depending on how far offshore the wave originates. But in other cases, the margin is razor thin. If the tsunami is triggered close to shore, the time between detection and impact may be measured in minutes. That's why detection alone isn't enough. It has to be paired with public awareness, fast communication, and local preparedness. Despite all the complexity behind the technology, satellite relays, undersea cabling, machine learning models, the core principle is simple: catch the wave before anyone can see it. It's a quiet science, one that hums in the background day and night, always waiting for the signal. And even though these systems can't stop a tsunami, they offer something just as powerful: the chance to move, to act, to survive. And as the wave races across the deep ocean with incredible speed, the next challenge becomes understanding how its power transforms when it reaches land. As soon as the earth trembles and underwater plates begin to shift, the countdown begins. While sensors in the ocean silently monitor the pressure of passing waves, another branch of science gets to work: the algorithms that analyze seismic activity and predict whether a tsunami is forming. This is the digital brain of early warning systems, built to detect the invisible, calculate the unimaginable, and send out a signal before it's too late. The process begins with a jolt, a sudden earthquake beneath the sea. Seismic sensors, scattered across the globe, immediately record the shaking. These sensors measure how fast the ground is moving, the depth of the quake, and its exact location. But the key question is whether that quake has the right characteristics to displace enough water to generate a tsunami. This is where early warning algorithms step in. These systems don't just look at the magnitude of the quake, they compare patterns, how deep it was, whether it occurred near a subduction zone, and what kind of motion was involved. Was it a strike slip earthquake, where plates slide past each other with minimal vertical motion? Or was it a thrust fault, where one plate shoved upward beneath another, the kind more likely to lift and displace an entire column of seawater? To make these distinctions quickly, the system relies on triangulation. That means data from multiple seismic stations is combined in real time to create a three-dimensional picture of what just happened underground. The more sensors that detect the event, the more accurate the prediction becomes. Within minutes, the algorithm generates a probability: high chance of tsunami, low chance, or uncertain. If the indicators cross a critical threshold, the alert process begins. In regions prone to tsunamis, like Japan, Chile, or Indonesia, emergency warning centers are staffed around the clock. Once the system flags a potential threat, alerts can be broadcast almost immediately. Governments send messages via TV, radio, and emergency networks. Automated text messages go out to phones. Coastal sirens blare. In some regions, warning apps push out updates before the wave is even visible to the naked eye. But this process isn't as straightforward as it sounds. The ocean is vast and complex. Not every large earthquake causes a tsunami, and not every tsunami behaves the way models predict. That's where the danger of false alarms enters the equation. A false alarm occurs when a warning is issued, but no tsunami arrives, or it turns out to be small and harmless. These events can erode public trust. If people evacuate multiple times and nothing happens, some may begin to ignore future warnings. The risk of complacency grows. But the alternative, underestimating the threat, is far more dangerous. In 1992, a small tsunami hit Nicaragua after a relatively moderate earthquake. It wasn't predicted. Over 170 people died. The earthquake's characteristics didn't meet the usual warning criteria. It was slow, shallow, and didn't register as dangerous, but it generated a deadly wave, catching coastal towns completely off guard. This kind of event exposed a blind spot in the system: tsunami-genic earthquakes that don't behave like the big ones we expect. To improve accuracy, scientists now use what's called nowcasting. Instead of relying solely on pre-programmed rules, the system watches in real time how the water behaves. If deep sea pressure sensors detect a disturbance, the model adjusts its prediction, sometimes overriding the seismic-based assumptions. It's a constant feedback loop between the sensors in the ocean, the data in the cloud, and the people making life or death decisions on land. But even the most advanced algorithms have to balance speed and certainty. Issue the warning too early, and you risk sounding the alarm for something that fizzles out. Wait too long, and you may lose the opportunity to save thousands of lives. It's a brutal trade off between seconds and safety. In some parts of the world, alert systems are connected to automated infrastructure. In Japan, for example, train lines can shut down the moment a tsunami alert is issued. Nuclear plants initiate flood protection protocols. Coastal floodgates begin to close. Technology responds faster than human reflexes, giving vulnerable systems a head start against the incoming wave. But even the fastest alerts mean little if people don't know what to do when they hear them. That's why early warning systems are only one part of a much larger puzzle. Public education, evacuation drills, and signage are just as critical. A siren can sound, but if no one knows which direction to run, the warning becomes just another noise lost in the chaos. As the tsunami races toward the coast, the best systems in the world are already working at their limits. Now, the outcome depends on one thing: how high, how fast, and how far the water is going to go. As the science of early warning systems has evolved, so too has the understanding that prediction alone is not enough. When a wall of water rushes toward the coast at the speed of a jet and with the force of 1,000 bombs, the question becomes not just can we see it coming, but also can we survive it? That's where the design of the world around us comes into play, an ongoing effort to engineer physical structures that don't just stand tall, but stand firm against the most violent force nature can deliver. In tsunami prone countries, you'll often find huge seawalls built along the shoreline. These towering barriers are designed to block or reduce the height of incoming waves before they reach coastal towns. Some are made of thick reinforced concrete, stretching for kilometers. In places like Japan, these walls can be 10 to 15 meters high, tall enough to block regular tsunamis, and strong enough to buy precious minutes. But seawalls aren't perfect. While they can shield against smaller waves, they struggle when faced with the full power of a major tsunami. Water has a way of finding cracks, climbing over barriers, and curling around corners with surprising ease. To help direct or control water, instead of simply trying to block it, some cities install tsunami gates. These are enormous metal or concrete structures placed at the mouths of rivers, harbors, or canals. Under normal conditions, they remain open to allow shipping and water flow. But when a tsunami warning is issued, the gates swing shut, sealing off inland areas from the surge. Think of them as floodgates, but on a far more aggressive scale. In some newer systems, the gates rise automatically when underwater pressure sensors detect a tsunami forming offshore. It's engineering in motion, fluid dynamics meeting mechanical speed. And while barriers try to stop the wave, some communities take a different approach, building above it. Elevated buildings are designed so that if water flows beneath them, the structure stays intact. These buildings often stand on sturdy concrete pillars, with the first floor left open or minimally walled, allowing water to pass through rather than push against. Hospitals, schools, and evacuation centers in coastal areas are increasingly being built on these raised platforms, an architectural lifeboat, quietly waiting for the moment it might be needed. But no matter how well planned, every design has limits. The biggest challenge is scale: a tsunami that climbs higher than the wall, or a wave that surges past the elevation zone, can still wreak havoc, and building such defenses everywhere is nearly impossible, financially, environmentally, and logistically. Some seawalls obstruct natural coastal beauty or harm marine ecosystems. Others may give residents a false sense of security, leading to slower evacuations when the real danger hits. After the devastating 2011 tsunami in Japan, which overwhelmed seawalls and led to the Fukushima nuclear disaster, the country faced a sobering truth. Even one of the most tsunami prepared nations on Earth could be caught off guard. The disaster prompted a complete rethinking of infrastructure strategies. It wasn't enough to just build higher walls. Japan began redesigning towns themselves. Entire communities have been relocated to higher ground. In places where that isn't possible, new evacuation towers have been constructed. Tall, sturdy platforms designed solely to give people a place to run when there's no time to reach inland hills. These towers are equipped with stairs, lighting, and emergency supplies, and are often placed in schoolyards, parks, or alongside busy roads. During drills, children as young as 6 practice reaching them within minutes. Japan also adopted the principle of multiple lines of defense. This means not relying on a single structure to hold back the sea, but layering protection. First a seawall, then tsunami gates, then wide roads that double as barriers, and finally elevated evacuation zones. Each layer delays the wave, reduces its energy, or redirects its flow, buying more time for escape. Elsewhere in the world, other countries are watching closely. Indonesia has begun building vertical evacuation shelters. Chile is upgrading coastal architecture to survive wave forces. The United States, particularly in the Pacific Northwest, is studying tsunami models to update building codes and infrastructure. But one thing remains constant: infrastructure alone cannot eliminate the risk. It can reduce it, slow it, shape it, but not erase it. That's why many coastal towns now combine physical defenses with digital simulations. Scientists run 3D models of past tsunamis across present day towns, identifying weak points and testing how different structures would fare under stress. From these virtual waves, new designs are born, designs that don't just stand against the ocean, but try to live with it. And as engineers continue to learn from each disaster, they push toward a future where cities aren't just built strong, they're built smart, adaptive, and ready. But of course, even the smartest design is still racing against time and water as tsunami resistant infrastructure continues to evolve. Another layer of protection lies not in concrete or steel, but in geography. Where we live, what lies beneath us, and how the land meets the sea all play a role in determining how vulnerable we are to the wrath of water. Understanding the landscape itself may be one of the most powerful tools in anticipating danger before it ever appears on the horizon. It starts with a fiery circle drawn across the map of the Pacific. Known as the Ring of Fire, this massive horseshoe shaped belt stretches from the west coast of South America, curves up around North America, wraps across the Aleutian Islands of Alaska, then dips down through Japan, the Philippines, and all the way to New Zealand. This region is infamous for its intense geological activity: earthquakes, volcanic eruptions, and inevitably tsunamis. That's because the Ring of Fire sits atop dozens of tectonic plate boundaries, where immense slabs of the Earth's crust are constantly colliding, sliding, or diving beneath one another. These movements build up enormous pressure beneath the seafloor, pressure that can release without warning, displacing water and sending out waves of destruction across the ocean. Some of the most devastating tsunamis in recent history, from the 2004 Indian Ocean disaster to the 2011 Japanese tsunami, were born along this volatile path. And because so many countries line the Pacific basin, from Chile and Peru to Indonesia and Japan, the potential for repeated impact is high. But the Ring of Fire isn't the only place to watch. Other zones like the Caribbean, the Mediterranean, and even parts of the Atlantic have their own hidden tectonic threats, smaller but capable of creating deadly local tsunamis. Still, not every coastal city faces equal danger, even within these zones. Geography decides who is most at risk. Cities built along flat, low-lying coastlines, especially those on river deltas, are among the most vulnerable. These areas often sit just a few meters above sea level, with wide open beaches and gentle slopes. While they might seem calm and idyllic, these very features allow tsunami waves to rush far inland without slowing down. The water doesn't crash and retreat as it would against a steep cliff. It floods forward, spreading out, swallowing streets and neighborhoods with astonishing speed. Take the Ganges Delta in Bangladesh, the Mekong Delta in Vietnam, or the Nile Delta in Egypt. These regions support millions of people, yet they're incredibly susceptible to flooding. A strong enough tsunami in the right place could roll across miles of flat terrain, leaving almost no time for escape. Coastal plains in places like Indonesia, Thailand, or even parts of California share similar risks, particularly where urban growth has crept closer to the sea. Topography also affects how energy from a tsunami behaves. Bays and inlets can act like funnels, concentrating wave energy and forcing it higher as it's squeezed into a narrow space. Cities like Hilo in Hawaii and Crescent City in California have seen repeat tsunamis amplified this way. Meanwhile, natural barriers like reefs, cliffs, or offshore islands can sometimes diffuse a wave's strength, protecting the coastline behind them, though that protection is never guaranteed. To better understand where the danger lies, scientists use historical tsunami maps, visual records that combine data from ancient sediments, eyewitness accounts, seismic readings, and modern satellite imaging. These maps show not only where tsunamis have struck before, but how far inland they reached, what paths they took, and how long they lingered. By analyzing patterns from past disasters, researchers can begin to identify likely hotspots for future ones. For example, areas that experienced repeated tsunamis centuries ago may still carry that risk today, even if they've been quiet in recent memory. Layers of sand found far inland in Japan and Indonesia have revealed ancient tsunami deposits dating back hundreds, even thousands of years. These ghost waves from the past remind us that absence of recent disaster does not mean absence of danger. Modern tsunami risk models now combine this historical information with real time data, population density, elevation, slope, and local building materials. The goal is not just to predict where a tsunami could hit, but to estimate the scale of the impact. Which roads would be flooded first? Which buildings would collapse? How long would people have to evacuate? In places like Chile and Japan, detailed tsunami risk zones are printed on public signs, mapped on smartphone apps, and practiced in community wide drills. And our but even in places where tsunamis seem like distant concerns, geography can surprise us. Underwater landslides off continental shelves, volcanic eruptions from island chains, or collapsing glaciers near polar coastlines can all send water racing toward unsuspecting shores. And as sea levels continue to rise, even modest tsunamis could reach farther and higher than before. Geography doesn't just tell the story of where we are, it shapes the future of how we prepare. From fault lines to floodplains, from coastal cliffs to urban sprawl, the land beneath our feet holds clues that could mean the difference between warning and tragedy. And while we can't move mountains or change tectonic plates, we can study the map carefully because sometimes the shape of the land knows the wave is coming long before we do. Even as maps grow more detailed and warning systems more precise, some coastlines remain eerily quiet. They sit along fault zones, lie near oceanic trenches, or face open seas known for tectonic unrest. And yet, they haven't seen a tsunami in decades, sometimes even centuries. These places, often overlooked, carry a different kind of risk, not because they're active, but because they appear deceptively calm. The Earth doesn't forget, but humans do, and that's where the danger begins. These silent coastlines are like loaded springs, places where pressure builds deep below the surface, slowly and invisibly, sometimes for hundreds of years, without obvious shaking or any visible signs on the surface. The plates continue to grind, press, and lock in place. And because no major event has occurred recently, there's a growing assumption of safety. Generations are born and raised without memory of disaster. Cities expand, tourism blooms, homes and businesses grow closer to the shore. The ocean becomes part of daily life, beautiful, calming, and familiar, until it isn't. One of the most striking examples comes from the Pacific Northwest of the United States, the Cascadia subduction zone. It stretches from Northern California up to Vancouver Island in Canada, where the massive Juan de Fuca plate dives beneath the North American plate. It's a tectonic fault, similar in structure to those off the coast of Japan or Indonesia, and yet the last major tsunami generating earthquake here happened over 300 years ago on January 26, 1700. Back then, there were no satellites, no seismic sensors, no written local records. The only surviving evidence came from Japanese coastal villages across the Pacific, where an orphan tsunami, a wave with no local earthquake, was documented arriving on their shores. Centuries later, Native American oral histories, drowned forests along the coast, and detailed Japanese records were pieced together to confirm the event. The silence since then has been unnervingly long. Geologists studying sediment layers and fault stress believe the region is overdue. The next event could happen tomorrow, or it could wait another 100 years, but the potential and the pressure are both there. A similar silence blankets parts of the Caribbean, where the eastern islands arc across a tectonic boundary between the North American and Caribbean plates. While smaller quakes and volcanic activity are more common, major tsunami generating events are rare. But that rarity doesn't mean the risk is gone. In fact, it's the quiet that makes some scientists uneasy. Islands like Puerto Rico, the Virgin Islands, and even the Bahamas sit near underwater fault lines capable of sudden displacement. Combined with steep underwater slopes, these regions could host powerful landslide triggered tsunamis, events that might come with almost no warning at all. Then there's the Mediterranean. Places like southern Italy, Greece, and the eastern coasts of Turkey rest atop one of the most seismically active regions in Europe. And yet, many communities built along these historic shorelines have not witnessed a tsunami in modern memory. The ancient city of Alexandria in Egypt was devastated by a tsunami in 365 AD. The same event struck Crete and other Greek islands. But as centuries passed, the trauma faded into legend, and the sea returned to its usual rhythm. The risk, however, remains, not erased, just hidden beneath time and sediment. Even parts of Africa's western coastline, which face fewer known tectonic threats, are not completely immune. Some researchers have pointed to the possibility of massive landslides from the volcanic flanks of the Canary Islands, a chain of islands off the northwest coast. If a significant collapse occurred, it could displace enough water to send a transatlantic tsunami toward the Americas, while also impacting parts of West Africa and southern Europe. Though highly debated and uncertain in timing, it's a stark reminder that geological quiet does not guarantee geological peace. What makes these silent coastlines especially dangerous is not just the lack of recent activity, but the psychological and infrastructural unpreparedness that often follows. When people believe an area is safe, they don't build escape routes, they don't practice drills, they don't install sirens or sensors, or educate the next generation about what to do if the sea suddenly pulls away. Buildings go up without elevation planning, emergency plans gather dust, and the memory of the last disaster fades into obscurity. But the earth keeps records differently, in its layers of rock, in the shape of river deltas, in the subtle warping of coastlines. Signs accumulate that something is shifting beneath our feet. When the silence breaks, it may be the first time in living memory, and the sea, so long seen as still and steady, may return with unimaginable force. From a distance, these calm coastlines look like paradise, but underneath, some may be ticking, not because they're noisy, but because they've been quiet for far too long. While many tsunamis come and go with terrifying force but limited reach, there are rare scenarios that exist in a different category altogether, the so called mega-tsunamis. These aren't just taller or faster waves. They're theoretical events that stretch the boundaries of what we've seen, based on massive geological shifts that could unleash waves hundreds of feet high and send them racing across oceans toward densely populated coastlines. They're not common, but they're not impossible either. One of the most talked about scenarios begins far from the United States, on the volcanic island of La Palma, in the Canary Islands, off the northwest coast of Africa. At the heart of this concern is the Cumbre Vieja volcano. Scientists monitoring the area have noted that one of its flanks, a large ridge of land built up from centuries of lava flows, is slowly becoming unstable. If a massive eruption or series of earthquakes cause this entire section of land to collapse into the Atlantic Ocean in a single sudden landslide, the consequences could be enormous. Computer models simulating such a collapse show a wall of water shooting outward in all directions. The immediate areas surrounding the Canary Islands would be hit first, but the wave wouldn't stop there. In a matter of hours, energy would ripple across the Atlantic. By the time it reached the east coast of North America, places like Florida, New York, and the Carolinas, it could still carry enough momentum to produce waves tens of meters high. While the models vary greatly depending on how much land falls and how quickly it moves, the sheer scale of the displacement is what makes it so concerning. The energy behind it wouldn't fade the way normal tsunamis often do. It would spread wide and deep, traveling thousands of kilometers before crashing into distant shorelines. But while the idea captures the imagination and headlines, many geologists urge caution. There's debate over whether such a massive flank collapse could happen all at once. Some argue the slope would break off in smaller chunks over time, releasing energy in slower, less catastrophic stages. Still, even the possibility of a single massive landslide is enough for researchers to keep a close watch on seismic and volcanic activity on La Palma. And although the event may be statistically rare, the warning signs are still being studied carefully. Across the globe, another mega tsunami scenario is quietly brewing beneath the waters of the Pacific Northwest at the Cascadia subduction zone. Here, the Juan de Fuca plate is slowly grinding beneath the North American plate. This region has remained ominously quiet for centuries, but the geological pressure building beneath it is massive. And when it finally releases, which experts agree it will, the resulting earthquake could rival or exceed the 2011 event that devastated Japan. Unlike smaller faults that release energy more frequently, the Cascadia fault is a giant stretching hundreds of miles along the seafloor. When it snaps, the uplift and subsidence of the ocean floor could displace an enormous volume of water instantly, launching a tsunami that radiates toward the US and Canadian coasts. Cities like Seattle, Portland, and Vancouver could be caught with only minutes of warning. The unique shape of the seafloor and the densely packed coastal infrastructure would make evacuation difficult, especially in low-lying areas. But the wave wouldn't just travel inland, it would also stretch across the Pacific, reaching Hawaii and even parts of Asia, depending on the event's size and direction. Scientists have used sediment analysis, core samples, and geological trenching to piece together Cascadia's past. Evidence suggests that these massive ruptures happen every 300 to 600 years. The last one in 1700 sent a tsunami all the way to Japan, where it arrived as a mysterious wave on a calm night, with no local earthquake to explain it. That event was strong enough to reshape entire coastal landscapes, and many researchers believe the region is now overdue. Still, the term mega-tsunami often brings exaggeration and fear. In movies and viral headlines, these events are shown as towering walls of water, hundreds of meters tall, swallowing skyscrapers in seconds. But in real science, the focus is less on height and more on energy, duration, and reach. A 10-meter tsunami that travels thousands of kilometers can be just as deadly as a much taller wave crashing closer to its origin. The destructive power lies not only in the wave's height, but in its momentum and the debris, flooding, and chaos it brings. While most mega tsunami scenarios remain hypothetical, they are not pure fantasy. They are possibilities drawn from real physics, observed geological patterns, and detailed computer models. And as technology improves, researchers are getting better at identifying early signals, refining risk zones, and updating emergency response systems accordingly. What's important to understand is that these rare, large scale events, whether triggered by volcanic collapse or a massive tectonic rupture, don't follow human timelines. They wait silently in the layers of rock in deep ocean trenches, building energy over generations. And while they may be unlikely in the short term, they are not impossible. Even with advanced warning systems, detailed evacuation maps, and years of scientific research, one of the most unpredictable variables in a tsunami disaster is human behavior. The ocean may follow the laws of physics, but people rarely do. When a warning is issued or a strange natural signal appears, like the sudden retreat of the sea, not everyone runs. Some freeze, some watch in disbelief, others assume it's a false alarm, and that hesitation, even if just for a few minutes, can become fatal. Part of the problem lies in how the human brain processes risk. When faced with something rare, massive, and outside of everyday experience, our instinct is often to downplay it. Psychologists call this cognitive dissonance, the mental discomfort of holding two conflicting thoughts. On one hand, you hear that a tsunami is possible. On the other, you look outside and see blue skies and a calm sea. Your brain struggles to reconcile that contradiction, and many people subconsciously choose the more comforting version. It probably won't happen to me. This isn't irrational so much as it is human. Most people have never seen a tsunami. Many live their whole lives without encountering any kind of natural disaster. So when a warning siren sounds or a government text message flashes across a phone screen, there's often a sense of disbelief. Some want to wait for more information, others are worried about looking foolish. It's difficult to imagine a giant wave sweeping through your neighborhood, especially when it looks like any other day. The effect is compounded in places with limited infrastructure. In some parts of the world, tsunami warnings still rely on word of mouth or radio. Sirens may be broken or poorly maintained. Text alerts might only be sent in one language or miss entire populations living off grid. In coastal villages without paved roads or organized evacuation plans, people may not even know where high ground is. And in overcrowded cities, confusion and panic can block escape routes long before the water ever arrives. Education gaps play a role too. In many countries, children grow up without ever learning the signs of a tsunami. They may know how to stop, drop, and roll for a fire, but they may not understand what it means when the ocean suddenly pulls away from the shore. In tourist areas, visitors may not speak the local language, may not understand emergency signage, or may not even realize they're in a tsunami zone. By the time someone recognizes the danger, it may already be too late. And yet, among every tragedy, there are also stories of those who noticed something and acted. These survivor accounts reveal how awareness, instinct, or just plain luck can make the difference between life and death. In 2004, when the Indian Ocean tsunami struck, there were children in Thailand who had recently learned about tsunamis in school. When they saw the water retreating, they screamed for their families to run. One young girl convinced dozens of beachgoers to flee inland, saving their lives. Elsewhere, villagers who had passed down oral histories of tsunamis, sometimes for generations, recognized the signs. In Indonesia, some remote communities remembered stories from ancestors about the ocean breathing in before screaming out. Those words didn't come from textbooks, they came from memory, and they saved lives. A fisherman in Sri Lanka reportedly saw fish flopping in the sand where the ocean had disappeared. Instead of collecting them, he shouted to others and ran uphill. He never saw his boat again, but he survived. These individual actions often go unnoticed amid the larger headlines, but they highlight a critical truth. It's not just about sensors, satellites, or alarms. It's about what people choose to do in those first precious minutes. And unfortunately, many hesitate because of mixed messages, past false alarms, or simply because they've never seen what a real tsunami can do. If a warning system has triggered several times without an actual disaster, people begin to ignore it. They assume it's just another drill or an error, and they stay where they are. When tsunamis move fast, even a short delay can be deadly. In cases where people wait for official confirmation before acting, the wave may arrive before help does. And once the flooding begins, roads become rivers, cars float, doors jam, cell towers go down. There's no reversing the decision once the water is already on its way. This is why early education, repeated drills, and local community awareness matter just as much as global monitoring systems. People must not only know how tsunamis work, they must believe it could happen to them. The science can warn us, but ultimately it's human decisions, moment by moment, that shape the final outcome. Long before any human senses danger, long before the ocean recedes or alarms go off, something stirs in the natural world. In forests, birds suddenly take flight in chaotic waves. In coastal villages, dogs bark uncontrollably, pulling at their leashes or fleeing for higher ground. On farms, elephants trumpet, twisting their trunks and running inland, ignoring commands. These moments aren't just scattered tales, they've been documented across centuries. Reports of animals acting strangely just minutes or even hours before a tsunami strikes. During the 2004 Indian Ocean tsunami, stories like these came from multiple countries. In Sri Lanka, elephants at a wildlife sanctuary broke their chains and ran uphill. In Thailand, tourists noticed monkeys scrambling inland, climbing trees and shrieking, even though the weather was calm and no visible danger was present. On the Andaman Islands, local tribes known for living close to nature survived the tsunami with minimal casualties. They had followed the animals. While these stories may sound like folklore, modern science has started looking deeper into why animals might have such early warning abilities. The key lies in what humans cannot perceive. Earthquakes, which are often the trigger for tsunamis, produce subtle changes in the environment even before the shaking is felt. There are low frequency vibrations called infrasound, waves that travel through the ground and air far below the threshold of human hearing. Some animals can detect these vibrations well in advance of the main shock. Elephants, for instance, have an extraordinary ability to sense low frequency sounds through both their ears and the sensitive pads of their feet. This allows them to detect rumblings in the earth long before we can. Dogs have incredibly acute hearing and may respond to sounds or vibrations that signal an impending quake. Birds have pressure sensitive systems that might pick up changes in atmospheric conditions. Even fish and marine mammals have been observed fleeing certain areas hours before underwater seismic activity begins. But it's not just about the ability to detect something, it's also about how animals instinctively respond. Unlike humans, who may overthink or hesitate, animals are driven by pure survival instinct. They don't wait for confirmation or wonder if others are overreacting. If something feels wrong, they move, and in the case of a tsunami, that instinct can make all the difference. Researchers have attempted to measure and analyze this behavior with mixed results. Some studies show that certain species exhibit clear, consistent signs of stress before major seismic events. Others suggest the evidence is more anecdotal and difficult to standardize. After all, animals can act strangely for many reasons, and it's not always linked to an impending disaster. Still, the volume of reports from across the globe, often from people with no connection to each other, keeps the question alive. What exactly are animals picking up that we're not? This curiosity has inspired scientists and engineers to consider whether biomimicry, the practice of designing systems modeled on biological processes, could help us build better warning technologies. If elephants can sense vibrations through the ground, could we develop sensitive seismic detectors that work the same way, distributed in coastal regions? If dogs react to subaudible frequencies, could a network of sound sensors pick up those same low frequency alerts? These ideas aren't science fiction. They're part of a growing effort to bridge the gap between biology and technology. Some experiments are already underway. In Japan, motion sensitive cameras and animal monitoring systems are being tested to observe behavioral changes in livestock. Seismic labs in Europe are studying how to integrate vibration sensitive materials into building foundations to detect the earliest tremors. The idea isn't to replace satellite systems or ocean buoys, but to add another layer of detection, one based on nature itself. Even if we can't replicate all the nuances of animal perception, there's still value in watching and listening. In many coastal regions, locals who live close to nature often take their cues from the animals. Fishermen in Indonesia have said they trust their dogs more than any radio broadcast. If the dog runs inland, they follow, and sometimes that decision is made faster than the time it would take to process an official warning. This behavior isn't limited to one species or one country. It's a global pattern. Horses stamp and neigh, cats flee to rooftops, chickens become restless, sea turtles abandon nesting beaches, bees vanish from their hives. Each animal responds in its own way, tuned to signals we might never notice but could someday learn from. And as we continue to refine our understanding of tsunami physics, seismic activity, and early warning systems, there's a growing recognition that nature has already developed its own alert network. We just need to learn how to listen. When the water finally stops moving, the silence is not peace, it's devastation. The land that once bustled with life is now buried under debris, waterlogged foundations, shattered glass, and broken memories. Survivors who barely escaped the wall of water now face another enemy, the aftermath. And in many ways, it can be just as deadly. One of the first things to happen after a tsunami hits is the complete collapse of normal infrastructure. Roads are torn apart, power lines are snapped like twigs, bridges that once connected neighborhoods are either gone or hanging by threads. Hospitals and clinics, if they're still standing, are flooded or overwhelmed. Communication lines fail. Mobile phones stop working. People can't call for help or even let loved ones know they're alive. And then the secondary disasters begin. Tsunamis don't just bring water, they carry oil, gas, raw sewage, chemicals, and wreckage from buildings. When that swirling mix settles, the result is often a thick, toxic sludge coating entire communities. Gas lines can rupture and ignite, starting fires in places that were just underwater minutes earlier. In some cases, flames spread across pools of gasoline floating on floodwaters, trapping people with nowhere to run. Firefighters can't reach them, roads are blocked, equipment is lost or damaged, and fresh water, the very thing needed to fight fire, may be either gone or too contaminated to use. But the threat doesn't stop with flames. Water sources are often poisoned. Wells are flooded with salt water. Rivers become a soup of debris and pathogens. Clean drinking water disappears. In the days and weeks that follow, this sets the stage for outbreaks of disease. Cholera, typhoid, and dysentery are common in post tsunami zones, especially in hot, humid climates. Mosquitoes breed in the stagnant pools, raising the risk of dengue and malaria. Sanitation breaks down. With no clean toilets and no way to wash hands, even minor infections can spread like wildfire. Food becomes another urgent concern. Coastal markets and farms are wiped out. Fishing boats are destroyed. Supply chains are broken. Relief takes time to organize, especially in remote areas, and when trucks finally arrive, they often struggle to navigate the shattered landscape. Helicopters drop aid where they can, but it's not enough. People line up for hours for a bag of rice or a bottle of water, and that hunger adds to the tension. Fights break out, desperation takes hold. Rebuilding begins as soon as the immediate danger passes, but nothing happens quickly. Bulldozers push aside debris, but behind every wall is another collapsed home, another pile of shattered belongings, another reminder of what was lost. Engineers must assess every structure for damage. Water systems need to be decontaminated. Electrical grids must be rebuilt from scratch. Schools are gone. Hospitals are overwhelmed. Even the simplest task, like restoring a single street, can take weeks, sometimes months. And for entire towns or cities, the timeline stretches into years. In some cases, it takes a decade or more before communities even resemble what they were before. But beyond the physical scars, there are the ones that can't be seen. Children who watched their parents drown, parents who held their kids one moment, then found themselves alone the next, survivors who clung to rooftops, watching as neighbors and friends were swept away. These memories don't fade when the mud is cleared. They settle into the mind, heavy and silent. Many who survive a tsunami experience post traumatic stress, flashbacks, nightmares, guilt over those they couldn't save. Entire villages carry the burden of shared grief, and healing becomes a long, fragile process. Counselors may arrive weeks later to help, but often there aren't enough. Mental health support, especially in poorer regions, is limited or non existent. People rebuild their homes, but inside they remain broken. The ocean, once a source of life, becomes a source of fear. Every wave is suspect. Every tremor in the ground feels like the start of another catastrophe. Yet, in the middle of all this, something else emerges, a sense of quiet strength. People come together. Families who lost everything find shelter with strangers. Communities organize food lines, share clothing, and rebuild from rubble. School children study under tents. Fishermen share nets and work to build new boats from scraps. There's mourning, but also resilience. Still, that recovery doesn't erase the lingering risks. Flooded buildings become breeding grounds for mold, and damaged foundations can collapse weeks later. In some cases, another wave or aftershock returns before full recovery begins, setting everything back again. International aid helps, but it can't reach everyone, and sometimes politics or poor coordination slow down critical response. The aftermath of a tsunami is not just a cleanup operation, it's a long, uncertain struggle for survival. For the survivors, the water may have retreated, but the real storm is only just beginning. The future of tsunami research is unfolding in real time, not just in labs or universities, but through satellites, underwater sensors, and high speed data networks that span the globe. The goal isn't just to understand these waves better, but to predict them earlier, respond faster, and possibly one day reduce their impact before they even reach the shore. Today, some of the most important breakthroughs are happening in orbit. Modern satellites orbiting Earth don't just take pictures, they scan sea surface levels with extreme precision. Instruments like radar altimeters can detect subtle bulges or dips in the ocean's surface, changes sometimes less than a few centimeters high. In normal conditions, these are just part of the ocean's natural behavior. But when a disturbance races across the sea, such as a tsunami triggered by an earthquake or underwater landslide, those small surface changes become clues. Even in the open ocean, where tsunamis are almost invisible to the naked eye, satellites can track them. The challenge is time. Tsunamis don't give much of it. That's where artificial intelligence is stepping in. Researchers are building AI models that process seismic data, satellite information, and deep ocean pressure readings at lightning speed. These systems learn from thousands of past tsunami events, simulating patterns and refining predictions with each new quake. The idea is simple. The moment a tremor is detected, the system runs calculations to estimate whether a tsunami has formed, how big it might be, where it's headed, and when it will strike. The sooner that prediction reaches coastal authorities, the more lives can be saved. Some of the most exciting work is happening underwater. Ocean floor sensors, called dark buoys, already exist and have been used in tsunami early warning systems for years. But future versions are becoming smaller, cheaper, and smarter. These sensors don't just detect pressure changes from passing waves, they're being redesigned to detect subtle pre tsunami signals, vibrations, shifts in deep current flows, and acoustic changes that humans wouldn't even notice. Connected in a vast underwater network, these next generation systems may one day alert entire continents before disaster strikes. At the same time, engineers and oceanographers are beginning to ask bolder questions. Could we not only detect tsunamis earlier, but somehow redirect or reduce them? It sounds like science fiction, and right now, in many ways, it is. The power carried by a tsunami, the energy of an entire seafloor shifting upward or collapsing, is beyond anything humans can counter directly. But small scale experiments are beginning. Some researchers are exploring how submerged structures or deep sea wave breakers might deflect or scatter tsunami energy. Others are testing how undersea bubbles, released in massive quantities from pipes or vents, could interrupt the smooth flow of a tsunami wavefront. The concept is that by disrupting the wave structure early, while it's still deep and traveling fast, the energy might be dispersed enough to weaken the impact when it reaches shore. Even if such systems remain out of reach for now, what's happening on land is just as critical. Computer simulations are advancing rapidly. Scientists can now run virtual tsunami scenarios for nearly every major coastline on Earth, factoring in local geography, building density, population distribution, and evacuation speeds. These models are helping governments plan escape routes, build shelters on higher ground, and decide where to place new seawalls or vertical evacuation towers. In Japan, for example, after the 2011 tsunami, entire towns were rebuilt farther inland, with new infrastructure designed using this kind of predictive modeling. Meanwhile, education is quietly becoming one of the most powerful tools of all. In schools across tsunami prone regions, from Indonesia to Chile to Hawaii, children now practice evacuation drills. Families receive illustrated guides showing warning signs and safe zones. In some countries, evacuation towers are color coded and marked in public squares, so tourists and residents alike know where to go without needing a second thought. The aim is not to instill fear, but readiness. And the research doesn't stop at Earth's oceans. As scientists learn more about tsunamis on our planet, they're also studying similar wave events on other worlds. Mars, for example, shows evidence of ancient shorelines and possible mega-tsunamis triggered by asteroid impacts. Understanding how these waves formed and behaved under alien conditions could, in time, teach us more about the forces at play here on Earth. Looking ahead, the most realistic path forward lies in layers of defense, early detection, fast communication, strong infrastructure, smart urban planning, and educated populations. No single solution can stop a tsunami, but together, these layers form a kind of shield, one that grows stronger with every new breakthrough, every new data set, every lesson learned from disasters past. And still, research continues to push boundaries, because at the heart of all this effort is a very human question. Can we stay one step ahead of something that has always struck without warning? With each new satellite sensor, algorithm, and evacuation drill, the answer may be shifting, slowly, from no to maybe. The ocean has always been a source of wonder, a vast shifting expanse that humbles even the strongest of human built machines. But beneath its beauty lies a force so raw, so unforgiving, that it can reshape coastlines in minutes and erase entire towns without mercy. A tsunami isn't just water moving, it's momentum unleashed. It's the memory of earthquakes, landslides, and underwater violence, carried forward in a rolling wall that doesn't blink, doesn't hesitate, and doesn't stop until it runs out of land. And yet, for all the devastation it brings, there's something brutally elegant about how it all works. The mechanics aren't hidden behind complex machinery or invisible processes. The ingredients are simple: rock, water, pressure, gravity, but the outcome is anything but. A locked tectonic plate, held for centuries under unimaginable tension, suddenly slips. That tiny release of motion beneath the seafloor becomes a cascade, water displaced, energy transferred, a ripple that becomes a roar. It doesn't always come with a warning siren or dramatic crash. Sometimes it begins with silence, a strange hush, a sudden wind shift. Then the water pulls away from the beach like it's taking a deep breath. People pause. Some even walk toward the retreating tide, curious. And then, with terrifying speed, the wave returns. But it's no longer a wave, it's a surge of energy packed into water that acts like steel. It lifts ships onto rooftops, it crushes homes into splinters, it carves new rivers through cities and farmland. And in the middle of all that chaos, it reveals just how little control we truly have when nature decides to speak. But knowledge changes everything. Every piece of data we collect, every wave we analyze, every drill practiced by a schoolchild in a vulnerable coastal village, it all matters. It doesn't stop the tsunami, but it prepares us. It gives us those few precious minutes to run, to warn others, to act, and sometimes those minutes are enough to make the difference between life and death. We've explored the physics behind these waves, the geology that sets them off, the technology that races to detect them, and the stories of survival and tragedy they leave in their wake. We've seen how not all tsunamis start the same way. Some are born from earthquakes, others from underwater volcanoes or collapsing cliffs. Some travel across oceans for hours, others strike just moments after they're triggered. But all of them remind us that Earth is alive and it breathes in violent rhythms. And still, most people living far from the ocean rarely think about any of this. Tsunamis are a distant concept, something they've seen in a documentary or heard about in headlines. But for millions who live along vulnerable coastlines, the risk is real, constant, and growing. Sea levels are rising, populations are expanding, coastal cities are pushing closer to the edge of the water with each new development. And as the past has shown us time and time again, the ocean forgets nothing. It simply waits. That's why awareness is so important. Not just for those who live near the shore, but for anyone who wants to understand how our planet works, how it breaks, rebuilds, and rebalances itself. Tsunamis are just one piece of that bigger puzzle, but they are one of the clearest, most brutal demonstrations of how powerful Earth can be when it shifts just slightly. So the next time you stand by the ocean and watch the waves roll in, remember what lies beneath. Remember that the same water that gently laps your feet can, under the right conditions, rise with the strength of an earthquake and the speed of a jetliner. Respecting that power isn't about fear, it's about understanding. It's about staying curious, staying prepared, and staying informed. That's what this channel is all about, diving deep into the science behind Earth's most mysterious and dangerous phenomena. If you've made it this far into the video, chances are you're the kind of person who's hungry to know more, who doesn't just accept surface level explanations, but wants to see the mechanics, the numbers, the hidden truths behind the headlines. And that's exactly what we do here. So, if you found this exploration into tsunamis eye opening, intriguing, or even a little unsettling in the best way, make sure to subscribe. Hit the bell so you never miss an episode. We've got so many more stories to tell, from the strange rhythms of the Earth's core to the mysteries buried beneath the ice of Antarctica, and together we'll keep peeling back the layers of our planet, one story at a time. Because science isn't just about facts, it's about perspective. It's about seeing the ordinary, the ocean, the wind, the ground beneath your feet, and realizing that within them are forces more powerful and more fascinating than anything we've built. Thanks for watching. Stay curious, stay safe, and respect the sea.